That's good. 7 to 8 in quantum. Okay, that's getting closer. Your camera over there or something else? Mm. Maybe someone else can put a camera here. What is that green box over there? I don't see it here on Zoom. Good. Do you need the mic?
Oh, yes, now it is. Perfect. So hello, everyone. Sorry for the delay. We are about to start now. So before we start, just some brief logistics. This is the tutorial on memory-centric computing. I am Geraldo. My clicker that's not working. Okay. There was all the way around. So I am Geraldo. I'm a PhD student at the Safari Research Group at ETH Zurich. And I've been working on processing memory, which is the topic that we're going to discuss today, since 2017. And I'm about to graduate, and I'm currently on the job market for industry positions. So I do research on processing memory and many other topics on computer architecture, including computer systems and hardware security. So before we start, if you want to get the materials for this tutorial, you can just scan this QR code here, and you can download all the slides that we are going to cover today over here. So I'm going to just give you a couple of seconds to scan the QR code, and you can find the material over there. Okay, hopefully everyone got it. Perfect. So the organizers of this tutorial is me, Dr. Mohammed, postdoc and senior lecturer at the Safari Research Group, Atarbek Ogun, which is also a PhD on research group, and Professor Onumutlu, which is going to give the first talk very soon. So what we have planned for the agenda today, we have an introduction talk by Honor, and then we have some talks related to processing memory and programming processing near memory architectures. These concepts are going to become more clear later on. Then we are going to have a short cough break since we are already delayed. Then we are going to move to processing using memory. Again, those concepts are going to be more clear later on, and the infrastructure to the research on processing using memory, especially FPGA-based ones. And then we're going to end up with an invited talk by Professor John Kim. This is, we have been doing these tutorials on processing memory for 2 years already, and we are going to move those tutorials now to workshops. We are going to have the first workshop on computer systems in ASPLOS, and we have a call for presentations in case you want to give a talk during the workshop. You can go to our website and fill up our form. We'll be glad to have you over there. This is happening in the end of March in the Netherlands, and then the deadline was actually at the 28th, but we are going to probably extend it a little bit. You can still submit, or yes. And then we are going to have the second workshop for memory-centric computer systems in ICS in Salt Lake in June. And then the third workshop on ISCA in Tokyo. So if you are online and you join one of those conferences, we'll be glad to have you over there. And again, we are going to have call for presentations for all of those workshops. So without further ado, we are going to have our first talk next by Honor, called Recent Advances in Processing Memory. Feel free to stop us anytime to ask questions. We are going to be glad to take your questions online as well. So thank you very much, and with Honor now.
Thank you, Geraldo. Do we have your, shall we do it from here or? Okay, let's see. Let me try my computer. But then I need some space over there. Now let's do that one. I mean, you have my slides, so. Guess while Geraldo's preparing, nice job. Welcome everyone. We've been doing these workshops since HPCA 2000, well, tutorials. They become workshops soon. They're going to become workshops soon since HPCA 2023. And they received a lot of interest from the community. In 2023, we had it with all major architecture conferences, all 4 of them. In 2024, we were with ISCA and Micro and a couple of other ones. And this time we're kind of our home is PPoPP, but clearly PPoPP is together with many other conferences. But the reason we wanted to do it with PPoPP mainly is because we want to enable a community on programming, especially of these memory-centric computing systems that are coming up. This is going to be one of the major enabling challenges for processing in memory systems. Okay, thanks, Geraldo. But as Geraldo mentioned, we're going to see more. We'll have more workshops coming up, and if you're interested in participating, giving talks. Okay, that was a mistake. How do I get back? If you're interested in giving talks, please email us or submit. I did swap displays. That was not what I wanted. I should have done exactly the same picture as this, but not the other one. Basically, I want what do you see, what do you get, but it doesn't matter. Yeah. Okay. Any questions before we start? This is going to be a short talk to introduce the rest of the workshop and some things that we have been working on recently. Hopefully, it'll be fun. Okay, today computing is to set the stage. Later, we're going to go into more details on the concepts that I'm going to present over here. To set the stage today, computing is bottlenecked by data. Data is really overwhelming a lot of components that we design. Memory, interconnect. Something wrong? Okay. Okay. Sorry, I messed up your setup over there. Okay, it's all good now? Okay. Yeah, basically, data is really overwhelming the components that we design. I think later, John is going to talk about, is it memory, is it communication? That's a great thing I'm looking forward to also. So data is really key for a lot of applications. Important workloads are all data intensive today. They require rapid and efficient processing of data, and data is increasing. And clearly, this is known, very well known in neural networks today, especially with large language models. Both data and computation requirements and communication requirements are increasing. It's true for other domains like genomics. We have a lot of work in this area, which is quite exciting, I think. In fact, data is increasing here, maybe even more so than machine learning. Depends a lot of genomic data analysis as well. So the problem is our current design principles when we design computers cause great energy waste because we're moving data a lot. This also causes great performance loss, again, because data movement consumes latency and bandwidth. And we're trying hard to alleviate the performance loss aspects and by building many, many different things into our systems, like hierarchies of caches, a lot of high bandwidth memories, networks, etc. And these are really complicating our system. So complexity is increasing so that we can tolerate the data movement latencies. And in turn, energy is getting wasted more and more because of the increasing complexity. So I think sometimes we forget how much complexity we add to our systems to tolerate these data movement issues. Okay, so if you look at computing systems today, they're all processor-centric. All data gets processed in the processor at great system cost, but we clearly have computing, communication, and memory and storage as three things. Maybe they need to be much more tightly integrated going into the future. This is my cartoonish picture system. If you look at an existing system, most of the system is dedicated to storing and moving data. In fact, if you do the calculations, more than 95% of the hardware real estate of a single node is dedicated to hardware elements that move and store data. Computation is a very small fraction of a system today, even in systems that do that have a lot of computation capability, like GPUs, for example. Yet the system is still bottlenecked by memory. So there are many results that are showing that data movement is a big bottleneck. This is one result from Google. It's about 10 years old now. It's ISCA 2015. They analyzed all of their data center workloads, and they showed that most of the time the processor is waiting for data. Okay, so that's performance. And then there's energy. This is again about 10 years old. This is from Bill Daly's presentation. This shows that computation and energy is not a big deal, let's say. If you look at computation energy of a complicated arithmetic operation, it's about 20 picojoules over here. You can argue with all of these numbers, but the trends kind of remain. And DRAM read or write access is about 800x worse over here. So 800 may be too much. Today, it's maybe 2 orders of magnitude. And this becomes worse as computation becomes more efficient, as well as computation becomes simpler. So a simpler arithmetic operation is much more energy simple than memory access. So you can see that the disparity is thousands of x. And today, people are trying to make things even simpler, right? With 4-bit machine learning, 2-bit machine learning, even lower binary neural networks, especially in energy-constrained environments. So the disparity between energy spent on computing, doing some arithmetic operation versus memory access is very large. And we're not even talking about storage here. If you go to like an SSD, you can multiply that number by about 10x or so. So we did a lot of studies to quantify the cost of this data movement on real workloads. This is a study we published at S+ a while ago. We found out that on average cases, you spend more than 60% of your total system energy on data movement on workloads that we examined over here. I will not talk about that, but maybe later Geraldo will talk about some, not just these workloads, but many different workloads that he's been working on. And on the machine learning models that are large, even on edge TPU, for example, edge machine learning accelerators, you get more than 90% of the total system energy spent on memory. This is just one example over here. These are not the largest machine learning models, but LSTMs and transducers over here. You see that most of the energy is really on the off-chip interconnect plus DRAM over here. And pushing the computation near memory reduces both of those energies significantly. Okay, so basically the fundamental problem we're targeting with the subject of this workshop is processing of data is performed far away from the data. How can we solve that problem? It's good to, I think, try to get new ideas in this domain. I'm going to talk about some examples, but it's good to, I think, brainstorm more. But essentially, we would like to enable computation with minimal data movement as much as possible, compute where it makes sense, where data resides. This could be in memory, in storage, in the sensor. The data is traveling in the interconnects, essentially everywhere, other than we want to enable capability of computation everywhere. Today, we don't have that capability except for accelerators and processors. Basically, we want to make computing architectures more data-centric. And there are many places where we can do computation, but we choose not to do computation in today's system. So we're really limiting ourselves to do computation in a very small fraction of this chiplet-based system today. And most of this chiplet-based system is still SRAM memory, if you think about it, and communication interfaces. Okay, so we're going to view memory as an accelerator to begin with, and we're going to offload computation to it. But in a maybe more future-looking model, memory is part of, different parts of the system are distributed agents that can communicate with each other and that can finish a task such that data movement is minimized. In what I'm going to talk about, I'm going to see memory as an accelerator, but I think going forward, we can actually do even more than this. But even with memory as an accelerator, the adoption issues are going to be one of the things that it's going to be important to keep in mind. And that's why we're organizing this at PPoPP over here, because programming is one of the biggest adoption issues, in my opinion, in addition to basically, if we want to send memory some computation and tell memory, can you please do this computation and return the results to me? There are many questions that we need to answer over here. How do you design the compute-capable memory and the controllers? How do you design the processor and communication units? How do you design the hardware-software interfaces, system software, compilers and languages and algorithms, and even the theory of computation? Again, I don't have a lot of time, so I don't want to go through these in detail, but there are a lot of interesting research questions that are happening in the field today, and in my opinion, there's more to come. Okay, so I should also say that this is not a new idea, and we should be cautious. People have been proposing processing in memory for at least 60 years or so. These are some of the earliest papers on this topic. If you know of some other earlier papers that are clear like this, please let me know. I'd be happy to change things. And these are beautiful papers, actually. These are proposing what's called processing near memory. Basically, they're adding logic next to memory chips or memory arrays. This is another paper around the same area, around the same time, basically. So what is different today? I think it's good to think about what is different today. There's also another question. Assuming that this is what we want to do today, which I believe it is, how do we get it adopted, right? In the past, I think we didn't have as much pressure to do processing in memory. Today, I think we have a lot of pressure. But also, in the past, we didn't think about adoption as much. Today, I think we need to think about adoption even more. So basically, today, what's different is, in my opinion, there are two things that are kind of squeezing us. One is we're having huge problems with the memory technology. Memory technology scaling is not going well. We're having issues like row hammer, row press that are causing bit flips. And all of these issues can be better solved if you have computation capability inside the memory. And DRAM manufacturers are already adding things inside their DRAM chips to do some small amount of computation to fix issues like row hammer and row press. I'm not going to talk about this in detail. We do a lot of exciting research, in my opinion, in this area. And it's good to see that in DRAM, people are adding computation to solve these issues. I think these are going to get worse. These issues will demand even more computation inside the memory. I think emerging technologies have similar issues, and they can enable new functions in memory, as well as they require more computation in memory to fix some of the issues that they have, like endurance. So that's the technology part. Technology is pushing us to do computation in memory. On the other hand, applications and systems are very much bottlenecked, as I described, by data access, energy, and data movement. And we want to maximize performance, energy, and sustainability all at the same time. For that, I think we also need computation in memory. So we're basically squeezed in the middle today with nowhere to escape. At least that's my perspective of the world. Okay, now I'm going to go into a little bit more detail. In this tutorial, we're going to cover processing near memory, processing using memory. I think these are two fundamentally different ways of doing processing in memory. Processing near memory is very similar to today's systems. In fact, today's systems are an example of processing near memory, except near is a bit far. Basically, you have memory and you have logic. You design them completely separately, but then logic may get closer and closer and closer and closer and closer to memory arrays. It could be inside the DRAM chip, but it's logic and memory are separate still, and they're separately designed. Whereas processing using memory is fundamentally different from today's systems, where you don't have logic. You forget about logic for some time. You take the memory circuitry and you understand, exploit, or enable better ways of using operational properties of these memory circuitry to do analog computation. So you exploit the memory circuitry. There's no different way of designing logic. So I'm going to talk especially about this one in this short talk, and Geraldo is also going to cover that. But keep in mind, there are programming issues everywhere, and there are adoption issues everywhere. This is clearly harder to adopt, processing using memory, in my opinion, except for some examples, some limited examples. Processing near memory, I think there are a lot of chips that are from prototypes as well as commercial chips from manufacturers that are doing processing near memory today. So it's easier industrially because processing near memory is what we do today in a sense, right? So that's processing near memory, that's processing using memory. We're going to talk more about that. Any questions? Okay. So this is the processing in memory landscape. Maybe this doesn't cover all of the startups, etc., but major players in the field. Clearly, we have 3D stacked memories that are getting better and better. We have logic layer underneath memory layers. That logic layer is going to get even better over future technologies. So I think there will be even more opportunity for hybrid bonding, for example, and in the future more with monolithic integration. So these packaging technologies will enable much more tighter integration of compute logic as well as memory. But even in existing technology, without, well, some of these are 3D actually. For example, there are manufacturers that have put processing units inside DRAM chips, DDR4 chips over here. Geraldo will later talk about that. There's also Samsung, SK Hynix, Alibaba. They've all built prototypes where you can do computation to accelerate, especially machine learning or recommendation type of operations. So there are real systems out there. That's the good part right now. And there are many other experimental chips and startups that are looking at, for example, processing in SRAM, processing in Flash, etc. So we're in a good place right now. And I think, for example, UPMEM is available. You can program it. You can actually develop programming models, etc. That's some of the things that we have been doing that we will talk about. And then today, I think we have better interfaces like CXL that enable computation offloading from the CPU to somewhere else. I mentioned this because I think this is also important from a system perspective, so that you can actually do better computation with better interconnect and communication interfaces. Okay, let me quickly talk about processing in memory. I think there's a lot to talk about here. I'm going to not talk about everything, but essentially, if we have a nice logic layer underneath memory layers, we can perhaps do a lot of nice computation. This is one of the earlier works that we did on accelerating graph processing using 3D stacked memory technologies. This is there's a lot of detail over here that I'm going to gloss over, but the paper's out there. You can read it. It's about 10 years old. And the idea over here is, can we design a system that can accelerate large-scale graph computation by doing near memory processing? Near memory processors consist of processors inside the logic layer that look like this. There are many in-order cores over here that are connected with some network. And then these cubes are connected to each other with some other network. And clearly, networking is also important over here, maybe to foreshadow John's talk over here. And if you actually want to do computation like graph processing, you partition your data across these cores, across the memory controlled by these cores, and you do communication. You basically ship functions to the data that you're trying to update. So basically, this is programmed using a remote function called programming model, message passing, essentially, which is similar to how distributed systems are programmed. And you do data partitioning to minimize the communication, especially across the cubes out here. So this is interesting, I think. And we showed in our paper that you can accelerate graph computation significantly. And you can check it out. And you can check out later papers that we actually did building on this one, which looks at formulating graph processing as sets, graph mining specifically as sets, and doing actually an ISA that is expressive in terms of set operations, so that you can actually nicely accelerate things using near memory processing and using memory processing. I'm going through this relatively quickly, but stop me if you have any questions. I think Geraldo is going to cover some of these in a little bit more detail. Let me give you another example of near memory processing. This is another work that we did with Google for some time ago, but I guess Geraldo will cover this one, so I'm not going to go into this in more detail. You're going to cover that, right? Okay. So there's a lot of opportunity for accelerating near memory processing, accelerating neural network using near memory processing as well. Okay, there's a lot more examples over here. I'm not going to talk about that. There's in storage also. These are some of our recent works. That was at ISCA 2024. There are many more examples in this updated paper that we recently pushed out to archive. If you're interested in a lot of examples of near memory processing, we cover a lot in this work. Okay, now let me go into processing using memory a little bit. I think the programmability challenges are even harder here, and also the generality challenges are even harder. But I will spend the rest of the 15 minutes on this topic, and then leave it to Geraldo to go into detail on both of these. So basically, processing using DRAM, exploiting the analog operational properties of DRAM, we can do a lot. That's the key takeaway. We can do bulk bitwise copying, initialization, zeroing, bulk bitwise operations, functionally complete, and or not majority nor NAND. We can do a true random number generation, physical unclonable functions, and more complex computation with a little bit more circuitry using lookup tables. At low cost, I already said this, and the idea is activating multiple rows concurrently performs computation. In sequence, it performs data copying and initialization. And it turns out these are possible even in off-the-shelf commodity off-the-shelf chips. Basically, without modifying existing DRAM chips, which are not designed for this purpose, by violating the timing parameters, we can get almost all of these functions. Actually, all of the top functions over here. Lookup tables, you can do it, but you support if you want to do computational lookup tables. Okay, so that's fascinating, I think. I'm going to show you very quickly, and Geraldo is going to go into more detail. Let's talk about something simple that many workloads do, which is data copy and initialization. MEMO and memcopy, for example, are two function calls that consume 5% of the data center cycles in Google data center, according to Google's paper that I mentioned earlier. And even when we do data copy and initialization, today we're very processor-centric. We don't do it on the memory side. We basically bring all the data that we want to copy over here, do the copy here, and write back the data. Whereas if you actually think about it, this is a function that could be easily offloaded to memory. And if you want to copy this page to this page, we can do it inside the memory. So that's the idea over here. And this brings about a lot of benefits that I will go through relatively quickly over here. And essentially, you can accelerate data copy by more than 10x and reduce the energy also by between 1 to 2 orders of magnitude. Let me give you the basic idea of RowClone. This is, again, old work, but I think recent works, as I will mention, has shown that there's even more potential, even in existing DRAM chips. So essentially, if you want to copy a source row to a destination row, if they are both in the same DRAM subarray, you first activate the source row, which brings the data into the row buffer. Now the data is actually nice and strong in the row buffer. And then you activate the destination row, which implicitly deactivates the source row and connects the row buffer to the destination. So by doing 2 consecutive activates with negligible hardware costs, you can do this copy. And we showed in our 2013 paper that this significantly accelerates copies. And at the application level, assuming you solve some of the system level issues that I'm not going to talk about, but we should be cognizant of and we should be solving, importantly, you can get significant system level benefits. Okay, so that's RowClone. Now let's talk about computation. So if you want to do computation, one primitive is to concurrently activate 3 rows. These are 3 rows in DRAM, ABC. I'm showing you only 1 bit line, 1 bit, but imagine the row is 8 kilobytes or 4 kilobytes or 16 kilobytes, depending on your row size. I'm showing you the sense amplifier they're connected to. Now, if you concurrently activate these 3 rows, A, B, C, you connect the capacitors to the bit line. And if at least 2 of those capacitors are charged, hopefully you get the charge state at the end. If at least 2 of those capacitors are discharged, you get the discharge state at the end. This is based on the charge sharing principles. In an ideal circuit, of course, with variation, you need to be more careful. But the final state is really a bitwise majority function. Now, this is beautiful, bitwise majority. You can express it as when C is set to 1, you get the OR, and C is set to 0, you get the AND. Now, this is becoming interesting. This is block bitwise computation model using majority, OR, and AND. And in the paper, in a later paper, we also said that you could take the NOT inversion of a row by actually connecting the inverted. Whenever you activate one row, you get the inverted part on the other end of the sense amplifier by connecting it to the same subarray. This is a little bit hard to do. It is actually expensive in DRAM chips, as later papers also showed. But I'm going to show you some results that it's already, you can actually get this function already in existing DRAM chips. Okay, so if you actually use those functionally complete, majority and not, and or not, you can accelerate applications, assuming you do the hard work to map the queries, for example, in a database into this underlying bulk bitwise computation substrate. And these are results, again, from the Ambit paper. So there may be other applications you can accelerate also that we have looked at some of them. We have not looked at all of them, but you can find them in the papers. So that's Ambit. So now, after we did this work, we started looking more into programmability of this. This is one work that Geraldo co-led, which is SimDRAM. I'll go through it relatively quickly. Basically, with this sort of substrate, you can accelerate essentially anything because it's functionally complete, right? Now, how do you expose it to the programmer? The software is another question. In this work, what we did was we expressed operations using circuits, schematics like this, and or not logic. And then we use majority inverter graphs to optimize them in terms of latency. And we converted that majority inverter graph to a sequence of DRAM commands. You can think of it as like a compilation step. And we stored a microprogram associated with a bulk bitwise operation that consists of those sequence of DRAM commands. Now, in the program, you insert these bulk bitwise operations, which is an issue, like who inserts this? We're going to talk about that in the next work briefly, but Geraldo will go into more. And when the operation is called, executed by the processor, it gets shipped to the memory controller, and the memory controller executes the microprogram associated with the operation. So this is a nice model, I think, nice framework. It could work for any operation in the end. If you want matrix vector multiplication, it works. If you want a simple multiplication, it works. You could make that operation anything essentially in the end, right? And we see significant performance and energy benefits, as you can see. Okay, so more recently, this is Geraldo's work that he presented at HPCA 2024. I'll go through this relatively quickly. Basically, there are some issues with this earlier model that I mentioned, the bulk bitwise model. And one of the issues is you're really operating on 8 kilobytes of rows or 4 kilobytes of rows. This is a lot. I mean, existing compilers don't target that size, right? And if your vector width, if you will, bitwise vector width is smaller than 8 kilobytes, then you're in trouble. You're wasting a lot of efficiency and as well as performance. So in this work, we take advantage of what is called fine-grained DRAM so that we can enable computation at the math granularity, a smaller granularity, like 512-bit granularity as opposed to 8 kilobyte granularity in DRAM. And this is enabled by changing DRAM such that it can operate at that granularity by segmenting the word lines, for example. And there's a lot of work in this area, including one from Ataberk that he presented at HighPeak recently, which is this one, sector DRAM. And if you actually do this, you can improve the utilization of the subarrays. And you can actually do other operations in the other subarrays. So it can pack different operations in a VLIW manner, potentially, or some other manner. You can think about it that way. We call it multiple instruction, multiple data. It's that manner. We added some more interconnects internally so that we can do reduction, because that's important for many operations. So this is near memory processing, actually. But you need actually not just processing using memory, but you want some other reduction operators over here. And I believe there's more that you need to add internally. And this eases programmability because now your vector width, if you will, is 512 or smaller, depending on your math size, which is really on par with the target SIMD width of many compilers and many ISAs. And I think this is one of the key contributions And I believe there needs to be more work to exploit this sort of substrate. But this requires, as you can see, changes to the DRAM hardware and also changes to the software stack. Okay, compiler support. I think Geraldo will talk more about this, but this is done all transparently to the programmer. The compiler extracts SIMD parallelism. It does code scheduling and data mapping, and it does code generation. We want to minimize the work done by the compiler. I will not talk about that in detail. And in the end, you get significant performance, energy, and especially performance per watt benefits. If you compare to a GPU, for example, the performance per watt is much better because you're utilizing all of the bits that you have in your subarrays, whereas a GPU has a lot of overhead still. GPU's control overhead is lower than CPU's, but it has a lot of overhead. Okay, now let me finish with some hope, meaning you can say, okay, these are very interesting things, but what are you smoking? Meaning, are there chips that are really capable of this? This is an exciting area, I believe, where we need to also investigate what can the existing chips do. And in recent works, we've shown that existing DRAM chips are already quite capable. This is Ataberk's work. He basically showed that by violating the timing parameters, you can mimic RowClone, building on compute DRAM work from Princeton. And he built this FPGA-based infrastructure where you can offload row copy and true random number generation operations to the memory controller from a RISC-V processor that's inside the FPGA. And you can do end-to-end studies over here, a little bit painfully, but if you're having pain, you can ask Ataberk to reduce the pain maybe. And you can get end-to-end results over here. And I believe you need more of these infrastructures like this to enable programmability at the higher level, as well as enable investigation of the system level issues. I hope people pick up on this. We'll be happy to help in some way. Okay, and this is real results using real violation of back-to-back activation. Basically, if you violate the activate to activate timing parameter, you can activate 2 rows in sequence, and you can do the copy operation, page copy operation. And these are real results of accelerating a micro benchmark on this real processor. Now you see very huge improvements because it's a very wimpy RISC-V processor that has very little tolerance, but these are real results in the end. Okay, so more on PIDRAM. More recently, we have shown that this is Ismail's work also in HPCA 2024. Existing DRAM chips are even more capable than what we had thought they were before. This work shows, actually, this work combined with some other work shows that one can copy one row into up to 31 other rows with almost perfect success rate, meaning almost perfect reliability. DRAM chip is not designed for this purpose, but we can copy one row to 32 other rows. If you're initializing a huge database, for example, you may want to do this. Almost perfect. The question is, of course, how do you do it perfectly? It'd be nice. But remember that DRAM chips are not designed for this purpose. You can perform operation with up to 32 output operands, and you can perform up to 16 input AND, NAND, OR, and NOR operations in real DRAM chips by violating the timing parameters. Let me give you the basic insights, and then Geraldo will talk more. So this is RowClone that I showed you earlier. Basic principle is back-to-back activates. Here, simultaneously activating rows can copy one row's content to multiple destination rows. Back-to-back simultaneous mini activates, let's say. Okay, so NOT operation, I've kind of alluded to this basically, but if you look at 2 subarrays over here, source and destination, they're connected through the sense amplifier. Essentially, that's a NOT gate. By consecutively activating source row and the destination row, you can get the complement of the source data in the destination row. So that's NOT. And finally, you can generalize this, and you can manipulate the bit-volume voltage that you have over here to express a wide variety of functions. So if you have A and B here and X and Y over here, if you activate all of them concurrently, and you can do that in real DRAM chips, as we have shown using our FPGA-based infrastructure that can violate these parameters. What happens is the voltage that you get over here is the average of A and B. The voltage that you get over here is the average of X and Y. And the sense amplifier essentially compares those two and drives the bit line and the other bit line based on that comparison. And if you set A and B appropriately, you can essentially get NOT, NOR, and OR functions. Okay, this is one example, but maybe Geraldo will go more into this. Is that correct? Sorry, he's going to talk more about the processing using DRAM. I think this is very fascinating. And the fact that you can do this in real DRAM chips is fascinating. And this is a paper that talks about these operations. So we repurposed our infrastructure to enable these studies much more efficiently. And we tested chips from major manufacturers. And this is the results that you get on real DRAM chips on multi-row copy. And you can see that we have almost 100% success rate. Okay, don't ignore the 0.02%. But I think that's the key, basically. How do you get it to 100% in the future? So there's more research to be done, but the good thing is the DRAM chips are already quite capable. So this is, and then data pattern, I'm going to skip some of these things, but you need to also vary the temperature, voltage, data pattern to see the sensitivity of this operation to different variables clearly. And this is AND, NAND, OR, and NOR. Again, Atabak will talk more about this, but you can see that you can get significant success rates. You can perform these operations with less success rate, but still not bad success rate. The key is basically, can we enable higher success rates? Now, of course, there's another question over here. Can we take advantage of these operations using commercial off-the-shelf DRAM chips with a programming model and applications built on top of things like PiDRAM type of infrastructure? I think that's also interesting, but it's a bit tougher, in my opinion. But it's good to think about that. OK, I'm going to skip some of these over here. There's more in the paper. And this is the multi-row copy. This paper analyzed multi-row copy in much more detail. OK, so basically the question is, what else can we do using commodity memories? And I think it's quite interesting. These are some old works that I will not talk about, and I'm already over time, I think. Geraldo forgot to stop me, probably. But basically, you can generate random numbers. You can generate better random numbers. And you can generate even better random numbers. Essentially, random number generation is a good example. You may think this is not interesting, but it's actually quite interesting, because one of the issues, I think, in security is you're moving data all around. And if you want to do security-critical computation, you don't want to move data, in my opinion. You keep the data in memory. And if you want to do some security-critical computation, you usually want to generate some random numbers. So if you actually have random number generation circuitry inherent in memory, and if you want to do security-critical computation, you want to have better random numbers in general. OK, and better random numbers. You can do physical unclonable functions. And I'm not going to talk about this, but maybe there will be talks. So before I start concluding, this was DRAM, but Flash is also very interesting. And you can do a lot of operations in Flash, as we have shown in real Flash chips over here. Similarly, you can do AND and OR operations in Flash. And Flash naturally supports NOT and XOR type of operations. So you can have a functionally complete substrate in Flash chips, and you can exploit that today as well. The key issue is, of course, system, like how do you design the system and how do you program it? OK, so I covered these two types. There's a lot more in this paper that we talked about, but let me talk about adoption. We're going to talk a little bit more about that in this tutorial, and it'd be good to get people's thoughts later during the day. There's a lot of adoption issues, clearly. You can build any hardware, and it could look great, but it may not be adopted. And we've seen examples of this in computer architecture many times. Clearly, what applications benefit? How do you write the software? What is the ease of programming? What kind of interfaces do we provide? And what kind of compiler and hardware support do we provide? What is the system and security support that's needed? There are a lot of issues like coherence, synchronization, virtual memory, isolation, communication interfaces. How do we design the runtime and compilation systems to make everybody's life easier to adopt this? And how do you enable infrastructures to assess benefits and feasibility? I think all of these are important, and there may be others as well. But I believe maybe the hardest thing is really the mindset issue that, and mindset and business issues that are kind of interrelated that we have in the compute memory dichotomy today. So very different companies do compute and memory. And we normally think of memory as something that cannot do computation. As a result, it's very difficult to move the interfaces so that we can actually enable computation. The good news is there's a lot of things that are changing in industry today also. So I think today is a good time to be doing research and development in this area. OK, let me conclude. I think we want fundamentally energy-efficient architectures. They need to be data-centric. We want fundamentally high-performance architectures. I think they also need to be data-centric. And if you want sustainable and also secure, I believe they also need to be data-centric. For this, we want to minimize data moment as much as possible. So I covered some recent advances in processing in DRAM. We're going to cover more. The good news is we can get orders of magnitude energy and performance improvements depending on the application. The second takeaway, I think, is unmodified DRAM chips are already capable of computation. And I believe memory should be designed as a combined computation and storage substrate, not as an inactive storage substrate. This means that design mindset and flow should change, not just at the memory level, but also at the higher levels of the stack. OK, so the future is bright, but we need to work hard on it. So as Geraldo said, we have workshops coming up at ASPLOS, ICS, and also ISCA. Because this is an important topic area, we wanted to actually have multiple workshops in different communities, as you can see. So if you're interested in presenting your work, please submit, and we'd be happy to consider it. Oh, I should also say that we open source essentially everything that I talked about today. And if you're interested in jumping into this area, you can start with the open source versions. For example, if you want to get your hands dirty and figure out what else can DRAM do, you get an FPGA, hopefully compatible with DRAM vendor. And you basically take the FCDRAM source code and try it, and maybe you'll find other functions. If you want to build a compiler for it, we'd be happy to help. Okay. That's all I have. I'm happy to take questions, thoughts. Otherwise, I'm going to give it. Okay. Let me just, yeah. Sure. Sure. Yes, S plus. Oh, okay. Yeah, so basically, no, there are no proceedings. It's basically in my talks, yes. Exactly. Yeah, basically, yes. If you present it, you can submit it anywhere. Yeah, yeah.
So, thank
you. Mm-hmm.
Two types of memory computing: one near memory and in memory.
Using memory, yes. Yeah, I say using it. Sure.
Gates.
Yes, yeah.
If you use technology A, approach A,
yeah. Yeah.
Yeah.
Yeah. I think that's a difficult question, but I mean, there needs to be some study. I agree with you. Maybe this is a great question to ask Geraldo, because we've been discussing this, and I think I agree with you. There needs to be some benchmark. It depends on the benchmark, of course. But if you're doing like bulk bitwise computation, the gain that you would get by going from near to using is a lot. Because, yeah, it's clear, basically. I don't know if you have an exact number. I don't want to put an exact number right. Yeah, yeah. Yeah.
I was thinking, what applications or benchmark suitable to adopt memory, near memory technology, or what other types of applications? Do you know if there's any study about this?
I think, I mean, not very comparative study. Maybe that comparative study needs to be done. I think that's missing in literature, in my opinion. Clearly, there are works that show the near memory. In fact, there are very comprehensive works like Geraldo's Damu work, and there are other works also that look at many applications and look at near memory, at least one version of near memory. There's also a lot of space. And there are also case studies that show that you can do using memory. But using memory tends to be limited to workloads where you can express nicely as parallel across many bits. So it's really bitwise, bulk bitwise computation. And whenever you want to do computation, you do it bit serially, right? So as long as you can express things that way nicely, you get a lot of gain. But there's no comparative study that I have seen. And that's maybe a gap that we need to fill. Very good. Yes.
Particular restriction in terms of access pattern, which is since they are basically SIMD engine, doing anything very regular is complicated. Like Honor mentioned, the district paper with program, there's a lot of random access. Implementing that in a process using memory manner would be extremely complicated. Not don't think possible, but like mapping regular patterns like that would be very complicated in a SIMD way. So that is one particular restriction.
Yeah, of course, graph is irregular, so other way mathematics is regular. So for ML like, it's another kind of fun.
Yeah, sure.
Thank you so much.
Yes, you're welcome. Yeah. In my opinion, they're aligned. Basically, I kind of rushed through those CXL slides, but basically, what CXL enables is a way of, I mean, CXL enables multiple things, but one important thing that enables is a way of offloading computation cleanly to something other than the CPU, right? And if you're offloading computation to a storage device or memory device or interconnect or NIC, it's nice with CXL. So it's good to have those developments in interfaces, communication interfaces, for sure. Okay, now I'll leave it to Geraldo because he has a lot of interesting things to say, but it's good to keep it active. So feel free to ask questions.
Let me just do some context switching quickly. Okay. Now they have that thing again. Sorry. Okay. So we are going to move a little bit into the specifics of those two types of processing in memory systems, processing near memory and processing using memory. I'm going to try to give a little bit of background on actually how we as designers should approach those two different type of systems. So Honor already mentioned processing near memory. I'm not going to explain it again. And the first question that you might ask is when we can employ this type of architectures, right? Application-wise. And there are much of research that I'm going to show in this slide. Honor already mentioned his slides as well. Some application domains that this type of processing near memory operation architectures are good at. Basically, whatever application that you have memory bottlenecks, you can design a processor near memory architecture around it to alleviate that data movement bottlenecks. And where do you find data movement bottlenecks in applications? In graph processing applications, in consumer workloads, in neural networks, DNA sequence mapping, databases, time series analysis, and so on and so forth. So the list is quite extensive. I'm going to show later on a benchmark suite that we put together of application from more than 70 domains that shows or collects those type of data intensive applications that can benefit from processing near memory architectures. The next question is, okay, I got my processing, I got my memory bound application. I'm going to design my processor near memory system, right? And then I'm going to get a lot of good benefit from that because we are completely eliminating that data movement bottleneck, right? However, it's not that easy, or it's not a one-shot gun or a silver bullet type of solution. There are several design restrictions that you have to take into consideration when you're developing or designing those type of systems, which I'm going to illustrate next. So there are different ways where we can integrate those processor near memory architectures in your memories subsystem. And depending on the way that you decide to design the processor near memory architecture, you're going to have different design constraints. So one example that was quite popular around 2012, 2015 was using logic layer into these stack memories to develop processor memory architectures. We have some commercial solutions from Samsung right now that exactly does something similar to this. Another solution would be to add some simple logic near the memory controller. Another solution would be to add some logic inside the DIMM of the form factor of a DRAM chip, or even nearby a DRAM bank. This is just an overview. I'm going to give more details on all of those later on. So the design challenge that I mentioned before, right? So the first design challenge is that when you're designing a processing near memory architecture, you have limited power and error budget to drive that logic. And depending on that substrate, you're going to have more or less area and power budget. Just as example, if you want to design, if you have a 3D stack memory, at the time of 2012, this memory from this Micron consortium called Hybrid Memory Cube was quite popular, HMC. It got discontinued, but then we still have something similar called HBM, where we have layers of 3D and a layer of logic at the bottom. So if you want to do computation over there, you have a memory device. And usually the logic space that you have to integrate some computation is dependent on the dimensions of the memory models. So basically what they do is we design the memory models and then in 3D, and then you project that area into a 2D plane. And then you have basically the space that you can add computation. But that logic die is not there for computation primarily. The memory manufacturers are not including that for you to put whatever you want. Basically what that is that for is to some interfaces like the PHY interface or some portions of the memory controller. They are going to be sitting over there so you can drive the 3D stack memory above. So after the memory manufacturer put the logic that they need over there, there is some free space available for you to include your logic. In the time of HMC, that memory space was around 4.4 millimeters square per 3D partition called a vault in that memory chip. At the same time, you have to drive that circuitry, right? So you also have to take into consideration the power budget that you are going to have per available per vault without having to redesign the circuits and increase the voltage level, for example, for the 3D stack chip. Another problem is, okay, I put my computation there, it fits. But how you dissipate whatever thermal or whatever heat that the particular computation is going to generate when doing computation, right? So usually DRAM use passive heat dissipation mechanism. So there is no active dissipation mechanism like a heat sink on top of your DRAM chip. And you don't want to, ideally, having to put a heat sink on top of your DRAM chip, right? That would include extra costs. So we need to also take into consideration how much heat your circuitry are going to generate, and how you're going to be able, and if you're going to be able to dissipate that heat using whatever passive heat dissipation mechanism inside the DRAM chip itself. The other problem is manufacturing. So, and this is mostly due to how the logic or CMOS-based manufacturing and the DRAM-based manufacturing evolve over the years. So usually when you're developing logic, you use a manufacturing process that is highly optimized for speed. So you want to reduce the clock frequency or improve the clock frequency, reduce the clock rate as much as possible so that you make your chip fast. And the DRAM chip uses a different manufacturing process, which is highly optimized for density. So you want to be able to put as many DRAM cells or memory cells inside the chip as possible. And if you try to design DRAM using logic, or if you want to try to design logic using the DRAM manufacturing process, usually there are trade-offs that makes one incompatible to the other or one impacting the other. So, for example, there is this quite old paper, but illustrates the process that if you want to design some logic gates using the DRAM manufacturing process, you are going to have a slow down your clock rate for your logics using the DRAM manufacturing process. And this is going to be, even though this paper is old, when I illustrate some of those processing and linear memory architectures, you're going to, that are commercially available right now, you're going to see they usually run at very, not very, but like megahertz of frequencies, where if you have like your out of memory processor, you can run that processor at gigahertz. And this is just a direct result of this challenge of manufacturing logic using DRAM manufacturing process. So in our works in Safari, I have a question. Sure. Yes. Yes, yeah, exactly.
The process, the access, because the closer the layer is closer to the sink.
Yes.
It's better than if it's far from sink.
Yeah, exactly. So we don't do much design in that direction in Safari. That is very manufacturing based. But what we see in the literature is that if there are, for example, some sensor-based processing memory solutions where they actually invert that like they add some sensors at the top of the design of the chip, and then some memory, and then some compute, and then some memory, and then they sandwich things around. And then there are other works that actually the people that actually works on thermal dissipation, they have ways of using some sandwiching where the heating goes from one layer to the other until they get to the very top. I'm not a very expert on that, to be quite frank. Yeah.
Physical location where power consumption.
Exactly. Yeah, exactly. Yeah, I think another one problem of actually manufacturing that is how you use the TSVs, like actually, because it's basically you need to like dig holes inside your layers to like go through the TSVs, and that overcomplicates also where you can put or place things. Any other questions related to this? Okay, great. So we mentioned Honor mentioned some of work that we did in Safari, and usually we take those constraints into consideration, which I'm going to illustrate next. Okay, so you have your application. Your application is memory bound. We have your constraint in mind, and now you're ready to design your processor linear memory architecture, right? So what type of system you are going to design? So there are three main ways. This is just in computer architecture, but you can also apply those concepts to design processor memory chips. So for example, you can design general purpose processor memory architectures, which usually uses some small wimpy cores that are programmable and can be used to accelerate different workloads. And we have examples of those from both academia and also industry. we can use fixed functional units. So you can you have your application. You know that application does something often, like general matrix vector multiplication or general matrix multiplication, and then you can design some fixed functional units accelerators and put this accelerator inside the memory chip itself. And again, we have examples from both academia and industry that does this type of design. The third one is reconfigurable architectures. So there are some solutions, bless you, that takes some FPGAs on CGRAs, not exactly entire board, but like some circuits that can be reconfigurable at the circuit level, and embed that near a memory chip itself. And again, we have examples from academia and industry. So I'm going to illustrate those design with next. We start with the general purpose programming course. So one example of this type of solution is Tesseract with Honor mentioned, which is a design that uses 3D stack DRAM to accelerate graph processing. So Honor already mentioned this, so I'm not going to go into details over this. Graph processing are bottlenecked by memory. 3D stack memories can be used to alleviate this bottleneck. And when we're designing Tesseract, we took the logic layer of the DRAM chip, took into consideration this area restriction and power restriction that we have, and then basically we decided to add some simple in-order cores in the logic layer of the DRAM chip to accelerate graph traversaling inside DRAM. So even though this design was targeting graph processing, since what we have here are very simple in-order programmable in-order cores, this Tesseract architecture can actually be used to accelerate other application domains as well. Honor already illustrate this. I'm not going to go into details on this again. So from industry, recently, since 2019, this French startup called UPMEM released these programmable DIMMs called DPUs, where they add some in-order RISC-like in-order cores processors near the DRAM banks inside a DIMM. And here is a little bit different from the Tesseract, because here we are not using 3D stack-based architectures to do or process near memory design. We use regular 2D-based DRAM chips. So I'm going to basically illustrate how this operates. So this in their currently in the current realization, those UPMEM memory DIMMs, they coexist inside the systems with conventional DRAM models that are used to store memory for your program. And then they use some accelerator model where you offload portions of a computation to those UPMEM DIMMs. This is very similar to how you program GPU. So you have to identify the kernel that you want to offload to these UPMEM DIMMs, write some code for these UPMEM DIMMs, and then move data from the conventional memory to this UPMEM memory, and then trigger the computation and then copy the output back from the regular main memory. As I mentioned, this is quite similar to GPU programming. So internally, this is a picture from the patent that the UPMEM company first filed for. So what we have here basically is your main SoC. This is your host CPU. And then you have some master interface that connects several DRAM DIMMs. And inside the DRAM DIMM, you have some DRAM banks and some in-order processor and some SRAM memory for instruction cache and scratch pad memory as well. So this is just another view of the same picture. So here we have your host CPU, your host DRAM memory, and your PN-enabled memory with the processing memory chips embedded to it. And inside those processing memory chips, we have either 8 or 16 different DRAM chips, depending if you have a 1 rank or 2 rank configuration. And inside each chip, you have a 864 megabyte DRAM bank per chip called main RAM or MRAM. Also, you have 8 DRAM processing units called DPUs. Again, this is a very simple in-order process, a RISC-V like in-order processor. and also with some scratchpad memory called working RAM, and some memory, SRAM memory for instruction allocation. So this is a view of what you would get if you buy those UPMEM chips. So basically, you have here a motherboard, and you have your regular CPU. You have your regular DRAM chip, and this is and then you have your PIN-enabled memory sitting in the DDR interface nearby your DRAM memory. So in order to program those UPMEM architectures, the UPMEM company released some SDK that have several APIs that allows you, for example, to manually move data from the CPU main memory to the PIN-enabled main memory, either using serial, parallel, or broadcast data transfer. Single meaning you move a block of memory for a single GPU inside the PIN-enabled memory. Parallel means that you move different blocks of memory from main memory to the PIN-enabled for multiple PIN-enabled memories. And broadcast is when you have one single buffer and then you move this buffer to across many different PIN chips inside the PIN-enabled memory. So in the current realization of this UPMEM chip, there is no direct communication across the PIN chips. So if you have to communicate across PIN chips, you need to move data across the whole CPU. And this can be challenged to do in workloads that requires some sort of reduction operation. So again, this is just an overview from their pattern on the UPMEM organization. I have some other illustration over here. And what basically we have in the process memory chip is some interface that is shared across the memory, the many GPUs inside the PIN chip to interface with the whole CPU. We have the 64 megabyte DRAM bank. We have some DMA engine that is used by the core to move data from the DRAM bank to the working RAM, which is some SRAM scratchpad memory. You have the instruction RAM here, and then we have 11 stages in other pipeline. So we did several analyses of this pipeline here, and basically, as I mentioned, they run at not a very high clock frequency. This is a direct result of that manufacturing constraint that I mentioned before, because those in other cores here are manufactured using DRAM manufacturing process. So this pipeline is not very fast. They use some fine-grained multi-threading. Oh, sorry, it's actually 14 stages. So, and then you have those 14 pipeline stages that are basically used to fetch the data from the working RAM, do computation, and write back data. So they have their specific, their UPMEM specific instruction set architecture, but it's quite, again, similar to some RISC instruction set architecture. And the UPMEM company also have put like some LLVM-based compiler used to create UPMEM binaries. So we have some lectures online on the UPMEM architecture. So basically, after this architecture was released, we got in touch with this company and we got access to those systems, and we started doing a lot of experimental analysis on top of this real processing near memory architecture. The first one was this benchmark suite that we want to understand what are the limitations of this architecture and what type of workloads would benefit from this. I'm going to briefly mention this PIM benchmark, which is a collection of 11 applications from, again, different domains, where we re-implement those workloads using the UPMEM SDK and deploy those workloads in the UPMEM system and collect a series of metrics to see how much they would benefit. And as you can see, you have workloads from as simple as vector addition or vector multiplication, or something more complex like bioinformatic workloads or some graph processing. So if you want question, sure. Yeah. Okay, sure.
Okay, some benchmarks just one benchmark. Okay, some benchmarks are multi-like or vector-like.
Yes, yes.
Right. Fine. Okay, sparse or dense. Okay, regarding the bioinformatics. Okay, is multi-like, you know, what kind of computation?
Yeah. Yes. So this workload, what basically does is dynamic programming. So you have a matrix and then you go through it. It's matrix. It's just binning basically. As creating the histogram. Yeah. So those workloads are quite actually. There's not much complicated here. Later on, I'm going to show some other workload that becomes more complicated. So those workloads are available online, but I'm not going to mention here they on details. So okay, so we did this initial analysis of those 11 workloads, but we keep developing workloads to see their benefits for this UPMEM system. So another set of workloads that we implement on this UPMEM system was classic machine learning workloads. So here is not the fancy neural networks. They are basically some decision trees, k-means, linear regression and logistical regression workloads. And then we did some experience with some machine learning training as well. And then for the machine learning training, we have some optimizations. And then we see that depending on the workload, we can have some very good performance benefits for these machine learning training workloads compared to CPUs and GPUs using this UPMEM architecture. So as I mentioned, like the workload just becomes more complex as we understand more and more the system. We also did some works on sparse matrix multiplication, sparse matrix vector multiplication on this UPMEM system for sparse P. We have some transcendation function support because the hardware of the UPMEM chip is quite limited to integer arithmetic operation. So if you want to do something like sine, cosine, would have to simulate that on software. So basically, we have some libraries that does that emulation and also propose some optimizations on top of that so that we can accelerate those workloads. We have other sequence alignment workloads, homomorphic encryption, reinforcement learning. This is for distributed stochastic descending algorithms, graph neural networks. Again, though, I guess those are just repeating. So this is the sequence analysis. So I'm just flashing this to show that since this architecture is called general purpose, as long as your application is memory bound, you can find a way of mapping the application to this UPMEM system. And that concludes the general purpose part. Is there any question related to that, of those workloads? Sure. Yes. Yeah. So since this is so first, I just want to point out that conceptually, we wouldn't want to do that, right? Because if the goal is to reduce data movement bottleneck, why you have to move the data from the host CPU to the UPMEM DIMMs, right? What does this accelerator model enables is to facilitate the system integration. Because if you want to use your UPMEM DIMMs as main memory for your system, you would have to add that to the same unified memory address space as the host main memory. This complicates several things like coherence, consistency. It creates a bunch of other different problems. But if it's just accelerator, you can just copy the data back and forth. So the idea here is that that you can as in GPUs, you can amortize that initial data copy from the input data with operating multiple times over that data. So basically, yes, you copy input and output out of that system, but still there is a bunch of intermediate data that stays inside the UPMEM chip, and then you don't move the data back and forth, as long as you don't have to do communication across the DPU chips. And in contrast, if you have to do the same thing on the host processor without UPMEM, the premise is that you would move the data from the input and output data from the CPU from the main memory to the CPU, plus those intermediate data as well would be moving back and forth CPU and main memory. So basically what we're eliminating is intermediate data movement here. Is there any other question related to UPMEM? Yeah. Of course, go ahead.
Part of the application will runs on CPU.
Okay, yeah.
Yeah. Good design. What's the balance? Why do you have to, let's say, assign the CPU, but have to offload PIM?
So if you're questioning like the design process is quite ad hoc, so I'm going to actually show. Yeah, I think I would just want to go through this slide. Yeah. Yes. So it's quite ad hoc. Like first you identify your profile application, figure out the requirements, and then you do the hardware software code design for that particular process. However, there is another aspect of the question which is related to offloading, right? So once you did the code design and you have the hardware set, well, your application is running. When you decide if you're going to offload a kernel or a instruction or a function to the CPU or to the processing memory architecture, right? That is for that we have solutions that are more methodical. So I'm not going to get into details of them here, but basically there are different ways of doing that. You can try to when the application is running, you can try to understand the access pattern of that application and figure out, for example, is that application generating a lot of less level cache misses and for a particular code region? If so, offload that code region to PIM. Another way, and what you are going to see that especially for fixed function units for the industry-based solutions. So since what they are basically doing is jam operate, and that simplifies a lot of things. Since they are doing basically jam operations for neural networks, and those neural networks usually use a very predefined set of frameworks that they are implementing, like PyTorch or TensorFlow, whatever, they can get the convolution layer re-implemented to the processing memory fixed function units that they have. And every time that you do a conv operation in your neural network, instead of going to the CPU, you go through the processing memory system. And that becomes much simpler because you can hook basically those function calls and dispatch them to the process memory architecture. But if you want to do this offloading in a general purpose manner, is more complicated because you need to understand the access pattern. Okay, so entering to the fixed functional units, I skipped some slides here. Basically, the idea here, and this is not different from processor-centric design, is that if you are designing something specific for a particular kernel, you can extract more performance benefits from that particular hardware that you are designing instead of using general purpose core. So this is just an example of that Google Workloads paper that Honor mentioned, that we took some applications from Google, like Chrome browsering, YouTube or Hangouts, video capturing playback, for mobile, and then we offload those applications or design processing memory solutions for those applications, either using general purpose cores or fixed function unit accelerators. And then you can see is that if you use fixed function unit accelerators, you can gain extra performance from those PIM cores. So, and this is not different from regular CPUs, right? If you can specialize as much you can specialize, the better, the more performance you can extract from the hardware that you're designing, right? However, to do that, what you need to do is first have a very good understanding of your application. You need to profile your application and understand the hardware requirements, the performance bottlenecks, and the energy bottlenecks of that application. And then we need to do some hardware software co-design to design a high-performance and energy-efficient application. So I'm going to showcase that for the machine learning inference models that Honor mentioned before. This is our work that we did again in Google. So it was after the consumer workloads one, where we went to Google and we got to their Google Edge TPU accelerator and their models, and then we did some profiling of those models. And basically what we saw is that those models could be divided into two different categories, or the layers of those models could be divided into two different categories. Memory-centric or processor-centric or data-centric layers. So here is just some profiling that we did. For example, these are some layers of CNNs, LSTMs, and these are two metrics, parameter footprint and reuse in flops per bytes. And as you can see, there are some layers that have very high parameter footprint, but very low reuse. And some other layers have lower parameter footprint, but higher data reuse. If you look at other metrics like MAC intensity across layers, you can also see that the MAC intensity significantly varies within and across different neural network models. So the main idea here is that the way that we are designing Google Edge, the way that the Google Edge TPU accelerator was designed, or we are designing Google, machine learning workloads, machine learning accelerators, is that we take different models that have different profiling characteristics, and we design a monolithic accelerator to accelerate those different models. What we do for this work is that instead of designing one big accelerator to fit everything, we design different smaller accelerators placed in different portions of the system, so either nearby the CPU or in the 3D stack layer of the logical layer of a 3D stack chip. And then during the runtime, depending on the characteristics of a given layer, we dispatch the computation to the appropriate accelerator. So the question here is that, like, how can you identify those layer properties? Again, we can cluster those layers into family of layers that are more compute-centric, and family of layers that are more memory-centric. And then during the runtime, we can design a scheduler that get the layer characteristics and dispatch them to the appropriate accelerator. So by doing so, we can significantly reduce energy consumption compared to the monolithic accelerator because you don't run into underutilization problems. No, this is just an example. You use other metrics. So we use there is parameter footprint, data reuse, MAC intensity. They are, I forgot the other ones, to be quite frank. But yeah, I think there was at least 5 to 6 metrics that we'll use, and we use those metrics to do the profiling and cluster them around. Okay, so by doing so, basically we can improve and utilize energy for the accelerator, and also improve throughput when you're doing the neural network inference. So this was the Google neural network model. So another example, which I'm not going to illustrate here, of fixed functional unit accelerators in industry, now is not in academia anymore, is what Samsung is doing. So since 2021, Samsung starts developing these processor near memory architectures targeting neural network inference. The first realization that they published was called PIM DRAM. They keep changing the names, but in the end, it's exactly the same idea. In their initial realization, they take the HBM chip, and this is a little bit different from what I mentioned from the 3D stack memory so far. So here they are not using the logic layer to add what they are going to use here is basically some MAC units. What they are doing is that we have X amount of DRAM layers in the DRAM chip, right? So they take some of those layers out, and then they repurpose those layers to have computation. So instead of having 8 layers that is pure DRAM, they basically have 4 layers that are pure DRAM, and then 4 other layers, which is DRAM plus some computation. So they do that because they want to make this device JEDEC compatible. They basically don't want to change the interface, so it's easier to adopt. And since they are Samsung and they are designing the chip from scratch, they have the power to do so, right? So here is basically the organization of those DRAM plus compute layers. Again, since this is basically accelerator targeting neural network inference, what they have is some float point matrix multiplication engines over here. And as you see, like this is a function, fizz functional unit accelerator, the instruction set is quite limited as well, because they are just going to be using this for neural network inference. This is just a view of the chip that they implemented. And as I mentioned, they keep work on this in this line with this PIM DRAM architecture. So they changed the name of PIM DRAM, functioning memory DRAM, to HBM PIM. And later on, they changed the name again to Aquabolt. So I don't know at this point what is the name. They keep probably this year they're going to move to another name. But anyway, in 2023, they did a presentation in Hot Chips where they showed that this architecture can also be used to accelerate transformers. The initial model was more for CNNs. And here, basically, they are showing that, as probably you know, the generative step of transformers like ChatGPT is quite memory bound because of matrix vector and vector multiplications operations. And they have basically 3 solutions to accelerate neural network models using this architecture. So the first one integrates that PIM DRAM architecture or the HBM PIM architecture in some AMD GPUs, and they show some marketing results showing that they can have significantly energy and performance gains when accelerating. I think this was GPT-2 at the time, if I'm not mistaken, using their HBM PIM organization. So the other solution that they proposed in that hot chip presentation was, instead of using HBM chips, they are using low power DRAM chips for doing on-device or inference, or like for your phone, for example. Again, the architecture is very similar to the architecture of the HBM PIM chip, but it's just that the form factor that they are putting those multiply and accumulate float point fixed functional units is different from the HBM one. Again, they show some good performance and energy gains when accelerating. Here, GPT-2, maybe the other one's another one. GPT-2 for those with this low power DDR PIM-based system. And then, someone mentioned CXL before. They also have their CXL prototype, where they have 2 solutions. So either you add the PIM chips at the CSL controller over here. At this PIM, in this presentation, they didn't provide much information what exactly the architecture of this PIM chip is. But later on in a paper last year, they have a paper giving more information, which I don't have in this slide deck over here. But again, it's not much different from the matrix vector multiplication engine. And so either you add the logic to the controller, or you embed the logic at the DRAM device that is inside the CXL memory interface itself. What basically this allows is for you to scale up the capacity of the PIM accelerator, right? Because you can have several of those memory expander in your chip. And again, this shows some good energy savings and increased throughput of using the CXL-based system compared to using just multiple GPUs. So I guess this is the Samsung examples. I don't know if is there any question related to the Samsung prototypes? Sure.
Couple of layers of HBM, another layers, couple of layers of typical DRAM.
Yes, yes.
So they follow the same strategy also in this.
In this design, yes.
This first correctly. That's the reason here.
Yeah, of course.
So for this two type of memory, the design should upload or offload whatever. Will implement, let's say, different type of operations if it is memory bound or compute bound. Is that correct or not?
It's not. So since all of these are basically doing the same thing, the software stack looks quite the same actually. So it's all offloading convolutions to this engine, and the only thing that they do is convolution. So is or matrix vector multiplication. So even though the hardware itself is different, the accelerator is quite similar. So, and they have pretty similar instruction set architecture and everything. So in the end, the computation that they are offloading is the same, but different scale of models, right? So like the CXL one you use for larger models, the LPDDR one you use for smaller models that are on the edge, and the regular HBM one used for medium scale models, but in the end, it's just transformers. Okay, so Samsung is not the only one doing this right now. SK Hynix also have their prototype. It's called AIM. Again, it's for neural network inference. And here is just a prototype of their chip. So basically what they are doing is adding some processing engines nearby DRAM banks over here. So I have an example here of their organization. Again, since all of this is to do matrix vector multiplication, the hardware of the engine itself is not that much different. Again, what they have here, a DRAM bank, and then you have some multiplier and adder tree to do MAC operations. What is different from the Samsung one is that they have some activation functions inside here, the accelerator itself, to do the full inference over here. So this was the AIM platform. This is from 2022. So, SK Hynix also have released other solutions. They have AIM-X, for example, but it does not differ so much from this over here. And they also have their own CXL-based architecture as well. So this is all to show that the memory manufacturers are catching up on this type of architectures, because we are having a push from those applications as generative AI, right? We're having a push from the application domain. So that was for the fixed functional unit. Is there any question related to fixed functional unit processed near memory? Okay, so if not, I'm going to move to the last one, reconfigurable architectures. The example that we are going to use from academia is this work that we did called NARROW for accelerating weather prediction modeling. So basically here, we are going to use this IBM-based CPU plus FPGA platform. And we are going to take the application, which is weather modeling, where we are going to offload portions of the computation to some reconfigurable logic that is nearby the FPGA design. This is just some results of doing that. I'm going to illustrate more the industry-based one, which is the Samsung IXDIM. So Samsung in 2021 have this paper where they have this FPGA, this DRAM GIM over here, and together with that we have this IXDIM buffer in the middle, which basically, I have a better picture later on, which basically is a system, FPGA-based system where we can reconfigurable the logic to do different operations. So initially they proposed this for recommendation on systems, and I have an overview of the design here. So basically we have your chip with a standard DIMM interface. You have your memory here, so 2 ranks per chip, and then we have a FPGA. And inside this FPGA, they create this architecture for recommendation systems where what basically they operate the chip in 2 modes, accelerator mode or non-accelerator mode. And what they basically are doing here is either array for the embedding operations when you're doing recommendation systems. So this was the XDIMM1. They keep working on this and using other applications on this system. This is for example, the same architecture, but since this is a FPGA base, they can do other logic. This is for sparse length sum, and there is another one for databases. So we have more lectures on the XDIMM available online. So what I just want to highlight here is not any particular design, it's just the scope that processor near memory can give to you. So again, designing processor near memory systems is not much different than designing whatever processor-centric system that you design today, right? We can design general purpose processor-centric systems, we can design finished functional units, processor systems, or reconfigurable architectures in a processor-centric manner. The main difference here is that we are going to move that design near the DRAM array, either in a 3D stack chip, in a FPGA-based system, in a 2D form factor, and then taking those constraints that I mentioned in the beginning of the talk into consideration, you're going to have your processor near memory design. So the next question is how you can do research on this processing near memory architectures. Workloads have been brought here many times. This was one of my first works on my PhD, which we were interested on understanding from application point of view, which metrics could indicate whether application would benefit from processing near memory or not. And then to do that, we create the simulator, which is based on ZSIM and Remulator, which allow us to do some scalability analysis on different types of processor near memory architectures and understand if that processor memory realization of that architecture would benefit in terms of performance or energy a given application. And then we run this to hundreds of applications and collect these applications into a benchmark suite, which is available online. It's called DAMove, and then you can run those applications over there. So another tool that can be used is, in case you don't have access to those chips, there are simulators available online that you can use to conduct research on processor memory architectures. So the Samsung HBA PIM1, for example, has a simulator available online, which is based on DRAM Sim 2. And also the UPMEM PIM chip has a very nice simulator, actually, called UPMEMulator, that again allow you to conduct research and even modify the hardware and see if what type of performance would you get if you modifying the internal organization. And this is the original paper that they have, which I think was running for best paper in HPCA last year. So this conduct my part for processing near memory. I'm going to briefly mention programmability of those architectures next before we go to the coffee break. Is there any other question related to processor near memory design? Okay, great. So let me do a quick context switch. Okay, that was surprisingly fast. Okay, so in the previous talk, I was mostly concerned about design. Now you're going to be concerned about programming, especially for the real-world applications, processing memory chip. So Ona already mentioned all of this, the barriers for adoption. I'm not going to go through it again. But basically, what I want to highlight is how you program a general-purpose processing memory architecture. So here I'm going to take into consideration the UPMEM base one, but the Samsung ones are not that different in terms of execution mode. So as I mentioned before, this is following an accelerator model where you need to divide the computation between PIM operations and non-PIM operations. And then you as a programmer needs to figure out which portion of the computation here is going to be PIM-based and split the data that for the PIM-based computation across the many process memory chips in your UPMEM DIMM, for example. Then you need to manually transfer the data from your host CPU memory to the PIM-enabled memory. You need to manually handle caching inside the processing in-memory chip. And finally, you need to move the output data manually again from the PIM chips back to the host main memory, and also consolidate consolidate those outputs as well. So if you need to do finalize a reduction, for example, you need to do that manually on the host CPU. So this, I'm going to flash a lot of code here. You don't need to understand the code. You just need to understand what that code means. So the UPMEM company have their own programming interface to program the UPMEM chips. And you as a programmer needs to use that interface basically to align input data. So the data needs to be aligned to 8-byte boundaries so that they fit inside a single PIM chip. You need to collect input parameters for your application. You need to distribute those input parameters across the different PIM cores inside the UPMEM PIM system. You need to launch the computation. You need to collect output results. You need to manage the scratchpad memory. You need to orchestrate the overall computation. But in the very end, what you just want to do as a programmer was to sum two buffer, do a reduction of a buffer and put in another buffer, right? So this is what I just want to highlight here is that there is a lot of code management that you need to worry about when a programmer is general purpose processing memory chips, just so that you write 4 lines of code. So the main takeaway here is that programming those general purpose processing memory cores induce non-trivial effort from the programmer. Basically, you need to learn as if a new programming model and interface from scratch. And even though that resembles programming interface as GPUs, for example, still you need to go through that, and that is error prone. Not only that, you need to have some understanding of the underlying hardware so that you can distribute the computation and manage the operations well in order to extract the performance from the system. So our goal in this work that I'm going to mention next is to ease the programmability for these general purpose cores by abstracting away the hardware components from the programmer. And to do that, we have 2 solutions. The first one is SimplePIM. So SimplePIM is a software framework that was presented in PAC 2023, which basically uses some software APIs for managing communication and processing, so you don't have to manually do that using the UPMEM-based APIs. So very briefly, the manager interface allows the user to understand or to map or to decide which input arrays in your application is going to be offloaded to the processing in-memory chip. For that, we have 3 APIs, look, register, and free. And then the communication interface allows the user to decide how you're going to distribute those input arrays across the UPMEM chips. So either using broadcast methods or gather scatter methods for host to PIM data communications, or reduce methods for PIM to PIM communications. So either reduce or gather. So the processing interface is based on a MapReduce based system where we have three main APIs. A map operation where you have inputs and then you have a map function, and then you generate as output an input array of the output array of the same size as the output, and then we map then we apply the map function to each element of the input array. We have a reduction operation, which takes an input vector and generates output array based on a reduction function that is applied. Or we have a zip function, which basically combines two input arrays into a third output array. So on top of that, we apply several code optimizations that we learn based on benchmarking that I mentioned later on that can extract better performance from the UPMEM PIM system. Like strength reduction, this is reducing the number of instructions in the application stream. Loop unrolling, avoid boundary tracks, function aligning, or adjusting the data transfer sites. So we take this framework and then we use that in our in the UPMEM PIM based systems to accelerate 6 different workloads from the PIM benchmark suite that are that can be implemented in this MapReduce based interface. And then we see that by doing so, this is a code example of a histogram using the UPMEM based APIs. Actually, the code is much larger. You can see the dot over here. But if you use the SimplePIM based implementation of the same algorithm, you can just call those APIs. So to do the manager of the input arrays, the data communication, and the computation itself. So the code is much simpler, and you don't need to do all of those manual data transfers or scratchpad handling by yourself. So by doing so, we can significantly reduce the number of lines of code that you need to write to implement those workloads. And because of our optimizations, we can improve or have comparable performance for some workloads, or even improve performance for some other workloads using this SimplePIM based implementation. So this is some weak and strong scaling results. So SimplePIM is available online. You can use this in your GitHub repository. And then after SimplePIM, we have further extend the framework, and we rename it. It's called Dapa now, and was presented in PAC the same year, where basically the problem of SimplePIM is that we have those 3 interfaces, right? Management, communication, and processing. Still the user needs to handle communication across the PIM chips, even though that communication is abstracted away using the APIs. The idea of Dapa improves on SimplePIM, but automatically handling any data communication inside the PIM system itself. And we do that by relying more on this MapReduce based infrastructure and using actually data parallel pattern APIs. So Dapa is composed of three main components: a collection of data parallel pattern APIs that the user can use to implement the application, a data flow programming interface that the user uses to operate on top of different input arrays, and then a dynamically template-based compilation. So as I mentioned, in Dapa, we are relying more on data parallel pattern primitives for this MapReduce-like frameworks. And what you're basically doing is skeleton-based programming. So skeleton-based programming is not a new concept. It's actually being used a lot for GPUs or multi-threaded CPUs and distributed systems. And in this skeleton-based programming, we use some predefined computing primitives that allows the user to tell the system how those different primitives would change the data during the execution of application. So in Dapa, we have 5 main primitives: map, reduce, filter, window, and group, where in SimplePIM we only have 3, right? Map, reduce, and zip. And the user can also combine those different primitives to do something more complex. For example, you can do a group and a window followed by a filter, or you can do a window and a group or a filter, or you can combine the three of them. And this basically allows you to express more and more computing primitives inside your application. So then the user uses those 5 different data parallel pattern APIs to implement the target application in a data flow manner. So this data flow manner, the main class that we provide to the user is what we call a pipeline, which defines a collection of transformations over the input data. And inside this pipeline, you have different stages, and each stage represents a data parallel pattern that is going to be executed in the UPMEM chip. And then here, basically, the data would follow sequentially. So implicitly, we are defining how data should move inside the application and hence across the different PIM chips inside the UPMEM system. Then the final thing that we need to do is compile that pipeline into the UPMEM code. So basically, we do that using 2 steps. So we have basically a template engine that takes UPMEM base template and use the information, extract the information from the pipeline and map that information to the appropriate place inside the UPMEM code template. Then we implement some dynamic optimizations where we dynamically compile each one of those pipelines in the application, execute them inside the DRAM chip or the UPMEM chip, and then move the appropriate output results to the host CPU or transparently from the user. Another optimization that Dapa have is in top of SimplePIM is that we divide, the framework also define the computation between CPU and PIM cores so they can cooperate on a given task. So this further improves performance. And this is there is a automatic way of doing that, and the user can also say do 20% of the computation in the CPU, 80% of the computation in the PIM core. It's not necessarily a code design. The user can put like it's just a parameter. Like I want to utilize 20% of my CPU. Exactly. And on the top of that, because I mentioned some alignment requirements, right? So in case your input vectors does not, there is some trail in the ends that would have to compute because of that alignment. We also automatically create code for the CPU so that that trail is executed in the CPU itself. So you don't offload that that unaligned portions of the data to the UPMEM cores. Basically, because you're doing this dynamically, we can do this type of runtime optimizations. So this is just an example for a vector.product of using Dapa. So basically, you have the computation as a vector.product. You as a user just need to figure out which data parallel patterns is going to be used to implement that computation. In this case here is a map and a reduce. And then you instantiate the pipeline for the map and the reduce for the operation. And then the framework dynamically generates the appropriate code based on the template to our UPMEM code, compile the code, and execute it on the UPMEM system. Again, we evaluate Dapa on a UPMEM-based system with workloads from the PIM benchmark suite, and we see that in terms of performance, we get some very good performance gains for hand-optimized implementations because we are using dynamic optimizations and doing CPU plus PIM collaborative execution. Also, in terms of lines of code reduction, Dapa significantly reduced the number of lines of code that you need to write to implement those six workloads from the PIM benchmark suite. So this is just a comparison to SimplePIM. I already mentioned some of them. Compared to SimplePIM, Dapa provides a higher abstraction level, so the user does not need to manually specify communication patterns, supports more parallel pattern primitives, and enhance optimizations with collaborative execution of CPU and PIM. So we conclude that Dapa improves in top of state-of-the-art programming frameworks for PIM. So this is not yet available online in terms of, it's not in your GitHub yet, because the paper is actually under review at this moment. But once it's done, we are going to make it online as well. And there is an earlier version. So this is concludes my programming processing memory system talk. I don't know if there are any question related to this, to Dapa or to SimplePIM. Okay, what is left there to be done is to basically extend these frameworks to other types of processing near memory systems, like the Samsung one, for example, or the SK Hynix one. Would be quite nice to generalize having the same interface for different backends, because in the end, all of those are processing memory systems. So if there's no questions, we are going to take we are going to be back at 10:30, and we're going to take a coffee break, and I hope to see you in 90 minutes. Thank you very much. Okay, welcome back. Sorry for the slight delay. I'm going to talk about next my favorite topic related to processing memory, which is processing using memory. Recall from Honor's talk, now you're going to use the analog operating principles of the DRAM chips themselves to perform some computation. So before I talk about that, I need to give you a little bit of background on how DRAM is organized and operates. So I'm going to go through this relatively quickly, but otherwise everything that I'm going to say next is going to sound like magic. The DRAM chip is hierarchically organized in a hierarchical component. At the top level of the hierarchy, we have what we call a DRAM mat. A DRAM mat is just a 2D array of DRAM cells. Those DRAM cells are horizontally connected to word lines and vertically connected through bit lines. So a bit line shares a local system amplifier, and a word line shares a local root decoder. So the next level of the hierarchy, we have a DRAM subarray. So a DRAM subarray is basically a collection of DRAM mats, and the DRAM subarray shares a global word line, which spans across the many DRAM mats inside the DRAM subarray, and some sensing logic, global system amplifier here, that is used to move data from the local system amplifiers to the I/O interface and eventually to the memory channel. So in order to access a DRAM row, the memory controller issues at least two main operations, activate and a read. So when issuing activate, the memory controller sends activate to a given source row inside the DRAM subarray, and this activate basically connects the DRAM cells inside that row through the local bit line. This is going to allow the DRAM cells to perturbate the local bit line and generate a voltage difference in the local bit line. So then the local system amplifier is enabled, and when this happens, the local system amplifier senses this voltage deviation in the caused by the DRAM cells. It amplifies this voltage deviation either to logic 0 or a logic 1, depending on how the data is stored in the DRAM cell itself. After that, the data is latched inside the local system amplifier and can be read using read commands. Then the DRAM issues a read command, a column access command, to portions of the data stored in the local system amplifier. In this command, basically moves portions of the data from the local system amplifier to the I/O interface and eventually to the memory channel. So as Honor mentioned, we can use these operation principles of DRAM cells to do some sort of computation. So we are going to start very easy doing some in-DRAM row copy operations by issuing back-to-back activations to the source and destination row inside a DRAM subarray. So when doing that, the first activate basically operates exactly as I mentioned in the background. We connect the source row to the local bit lines. The data is latched and amplified by the local system amplifiers. And after that, we issue another activate to the destination row. So this basically connects the destination cells to the local bit line and hence to the local system amplifier. And since the data that was latched here in the local system amplifier has a higher drive than the DRAM cells here, this data is going to be written back at the destination row, hence performing the in-DRAM row copy operations. So likewise, we can do majority of 3 operations, but now we are going to simultaneously activate 3 DRAM rows at the same time. When you do that, the 3 DRAM cells simultaneously perturbate the local bit line. And what we have as local system amplifier basically is a differential circuit, which pulls the voltage level to the majority of the voltage levels that are stored in the 3 DRAM cells before. So here, the majority of blue, and yellow is going to be blue. And then at the end of the computation is stored in the 3 activated DRAM rows. So again, as Honor mentioned, before we did all of this in simulation conceptually, and recently we have been conducting some studies on commodity off-the-shelf DRAM chips and we saw the commodity off-the-shelf DRAM chips are capable of a subset of those in DRAM row copy and majority of 3 operations by violating the DRAM timing parameters. So Onur already covered this. We can do NOT operations and NAND or NOT operations using this principle. So, okay, we started very simple. We start by doing in DRAM row copy and in DRAM majority. But what about something more complex, as addition or a multiplication operation? So in the SimDRAM work, we show that we can generalize this framework or these operations to compose more complex operation using a 3-step framework, which Onur already mentioned. I'm just going to illustrate how that framework actually operates. So the framework takes as an input and or not based representation of your target operation. So here, for example, we have a RIP carry header, and then it generates the equivalent circuitry using majority NOT gates. And we do this because what we are actually doing when you're doing in DRAM operations is a majority of 3, right? So when you convert the AND gates to majority gates, we can have less number of triple row activations to do the computation. So the next thing that we need to do is to traverse this graph, this circuitry here, node by node, and issue the triple row activations based on the inputs of the nodes. So here I'm going to guide the example here. So basically, we activate the first majority node, which involves rows A, B, and carry in. When you do the triple row activation, you're going to have carry out, which is going to be the majority of blue, blue, and yellow, which is again blue. Then we move to the next gate, which does activation of A, B, and carry in again, but this time around A is negated. And so we are going to have the majority of yellow, blue, and yellow, which is going to be yellow stored in the temporary row. Then we go to the third node, which involves the previous computation store for the first node and the second node, and also A again. And then this means that you're going to activate rows with blue, yellow, yellow. Again, it's going to be yellow. And then in the very end, we are going to have one row with yellows, which is the sum row, and one row with carry out, with blue, which is going to be carry out. Yellow here means 0, blue means 1. So the result of 1 and 1 is going to be 2, 1, 0 here. You physically negate. So I don't have a slide here, even though I should. Basically, yeah, I'm not going to have any slide here. So as Onur mentioned, what this box here basically is 2 back-to-back inverters, right? So what we actually do is we take one side of the inverter and then reroute that side to the inverter to the DRAM cell here. So the DRAM cell now have 2 access transistors. One to access the data, the regular data from the cell, which is the not negated value, and another access transistor that is actually the rerouting of that inverter back to the cell itself. So if you access we call them N word line and D word line. If you access the N word line, basically what you're getting is the output of the inverter from the system amplifier. So you actually like physically negating and writing back to the cell. It's not is special in the sense that you need to have this rewiring, but the cell itself is still DRAM cell basically is an access transistor and a storage capacitor. That the storage capacitor is the same. We don't change it. We just have another access transistor that comes from the other end of the local system amplifier. This is for simulation base. So it's a repurpose, but in the commodities of the shelf, basically what we have is that inverted data is written to basically what we have in DRAM is like we have one subarray. It's called an open fold architecture. So we have one subarray with a DRAM cell, the local system amplifier, and then another subarray. Basically, neighboring subarray shares the same set of local system amplifier. What we do is basically, if you do the regular activation, the data, half of the data is going to be negated and in the other end of the local system amplifier. Usually we don't read that because you're interested in only on the regular data, but then we can just use the data for the NOT operation. When you actually show this result here, came from NOT operations, there is asterisk here actually, because it's in neighboring subarrays. It's not exactly in the same subarray. And it's all because of this folded architecture, open architecture basically, where the neighboring subarrays shares the local amplifier. Okay, hopefully that was more or less clear. Okay, so basically, if you operate DRAM as this, we're going to use the DRAM chip as a very wide SIMD engine, where you're going to have as many SIMD lanes as DRAM columns inside the DRAM subarray. So we do this work, or we implemented SIMDRAM in the Gen 5 simulator. We use it to accelerate, to implement 16 complex in-DRAM operations, include addition, multiplication, division, and we use those implementations to accelerate 7 different workloads. And we see that in terms of throughput, SIMDRAM significantly improves compared to CPUs and GPUs, and also in terms of energy efficiency and end-to-end speed up for those 7 applications. Okay, all of that is very nice, but this type of SIMDRAM framework or substrate is not very efficient. And this is because of the rigid computing ground layers that you have inside the DRAM subarray. So this caused 3 problems: SIMD underutilization, limited computed support, and challenging programming mode, which I'm going to briefly illustrate next. So basically, we took the SIMDRAM framework and then we run some applications to understand the utilization of those applications in this framework. And we compute what is called the maximum vectorization factor, which is basically the maximum number of scalar operands that fit in a SIMD register. So ideally, you want to have as many scalar registers inside the SIMD register for the substrate as the number of DRAM columns, so 65,000 per loop. We collect these vectorization factors in loops of 12 different applications for different domains. So those are like matrix operations, convolutions, image video decoding, PCA for data mining. I think this is basically that, and some stencil operations. So any value above in this plot, any value above the green line means high utilization. This framework is operating well. Any value below this line means low utilization. The architecture is not operating very well. So we make some observations. We see that the amount of SIMD parallelism inside the application significantly varies inside and across different applications. And we see that very small fraction of loops inside the application have enough SIMD parallelism to fully utilize those 65,000 columns inside the DRAM subarray. So you're going to end up in underutilization problems. The second problem is limited computed support. So in that vector example addition, we have 2 arrays or 2 rows operating and generating another row of data, right? What if I want to reduce that row into a single scalar value? Since there is no direct communication across different DRAM columns, I cannot not operate into that reduction operation. And implementing a communication across the different DRAM columns, like all-to-all communication, interconnects would require very high area cost inside the DRAM subarray. Third, these have a challenging programming model. Basically, it's another similar example of that of how you program the system. Basically, you as a programmer need to manually generate assembly-like program instructions to this framework, which means that you need to map and align data structures to our subarray boundaries, identify subarray boundaries, manually unloop loops, and map the C primitives to processing using DRAM operations, and also orchestrate data movement. So this is the example of the same code here, using the PPoPP instructions for a predicated and sub operation, and this is not trivial to write. So basically, the problem that you're dealing here is that processing using DRAM's large and rigid granularities limits the applicability and efficiency of processing using DRAM substrates, and are going to design a framework that or a substrate that can overcome those issues. To this end, we use proposed MIMD DRAM, which uses this idea of fine-grained DRAM activation for processing using DRAM, which Honor already mentioned, is the ability to actually access only one of those DRAM mats inside the DRAM subarray, and these have been proposed for energy efficiency DRAM access before. Honor already mentioned these slides. This gives us 3 benefits. It improves SIM utilization, allow us to implement reduction at low cost, and allow us to map vector ISAs to process using DRAM primitives. I'm going to mention more the implementation of these in details. So basically, we have to do some modifications to the DRAM subarray to allow us to individually access those DRAM mats when we are doing the process using DRAM operation. And also, we have to do this intermat interconnect that allow us to move portions of data from one DRAM column in one mat to another one. We also implement some control units because now the control is more complicated. We need to basically dispatch, keep a scoreboard to see which one of those mats in the DRAM subarray are being used for a process using DRAM operation, and dispatch data independent instructions depending on the utilization of the scoreboard. So this control unit is implemented in the memory controller. We also implement some compiler support for code identification, code scheduling and data mapping, and code generation using LLVM. So those are 3 LLVM passes. So the first, I have this repeat. So the first pass here is responsible for code identification. So basically, we took LLVM auto vectorization loop engine, and we repurposed it to generate PIM instructions with the maximum vectorization length possible for a given loop. And this basically depends on the loop trip count of a given loop in the application. Then we use some code scaling and data mapping to add some metadata to those vectorizable loops to tell the hardware if that particular loop needs to be executed concurrently inside the same DRAM mat, or they can be executed sequentially or concurrently across different DRAM mats in case they are data independent. And the third pass is basically for code generation. We modify the 886 backends to generate those PPoPP instructions in the application binary. So another thing, so for this binary to be able to run, we need to tackle several system integration issues. The one that I'm going to highlight here is data allocation and alignment. So basically, from the application point of view, well, we need to guarantee that 2 arrays are aligned inside the single DRAM mat, inside a single DRAM subarray, inside a single DRAM bank. However, the operating system does not cannot guarantee that data is going to be properly aligned like that natively. And this is because of the several layers of translation. Then a virtual page goes until we reach to a DRAM row. So basically here we have different memory allocations API on the operating system, right? So for example, we can use a malloc operation to allocate data. So if you do a malloc operation, there is no guarantee that virtual pages are going to be aligned, neither that physical frames are going to be aligned, nor that DRAM rows are going to be aligned. If you use allocation APIs from the main-align family of allocators like POSIX, MemAlign, you can guarantee, the operating systems can guarantee to you that the virtual pages are going to be aligned, but that is still not guaranteed that the frames are going to be physical aligned or that the DRAM rows are going to be aligned. Finally, you can use huge pages. Huge pages guarantee to you that the pages are going to be aligned in the virtual address space, that the frames are going to be aligned in the physical address space. But since there is still some interleaving that the physical frames goes through until they reach DRAM, there is no guarantee that the physical frames are going to be contiguous inside and properly aligned inside the DRAM subarray. So none of those allocators are available in the operating system can guarantee that your data is going to be nicely aligned so you can do the process using DRAM operations. So to fix that, basically, we provide a new allocator, so a new PIM malloc operation, which allows the operating system to allocate physical frames align physical frames that are going to be also aligned across the different subarray boundaries inside the DRAM chip. And to do that, basically, we combine huge pages, which gives alignment for us from until the physical frames, to reverse engineering information about the DRAM interleaving, which let us know where a given frame is going to be mapped inside the DRAM subarray. And we combine that with our allocation algorithm that allows the application to tell that a particular array is needs to be aligned at a given boundary depending on another array allocation as well. I'm not going to go into details over here because it is a little bit involving, but basically the takeaway is that with these two information here, with huge pages and reverse engineering DRAM interleaving information, we can guarantee that data alignment. So, okay, there is more information of that in the paper. On already briefly mentioned that by doing MIMD RAM, we can accelerate nicely those 12 real-world applications. So, okay, so this is for arithmetic operations. What about more other type of operations, right? So we have been doing processing using DRAM operations using row copy operations, majority Boolean, simple Boolean operations, majority of three base, and now arithmetic operations in both SIMD or MIMD manner. What about operations that cannot be easily implemented using arithmetic operations, like transcendental functions, like sine, cosine, logarithmic operations, right? To implement those operations in DRAM, we use lookup tables. The idea here is quite old. Instead of doing the computation, we are going to pre-compute the data and store in DRAM, and then we are going to replace computation with memory access in a lookup table operation. To support that, we implement Pluto look query operation, which basically maps a lookup table inside the DRAM array and adds some access circuitry inside the DRAM subarray to figure out if there is a match between the currently accessed data and input query that you want to query from the lookup table. So I was not going to go into details on how this goes, even though I have a lot of animation here for the interest of time. But basically, it's a lot of implementation. Basically, by doing so, we can accelerate operations that neither SIMD-RAM or MIMD-RAM can accelerate on, and then we can have some nice performance improvements compared to CPUs and GPUs for operations that require those transcendental functions. And there are more information online. So processing using DRAM is not limited to that as well. I want to mention that we can do other things like true random number generations, better true random number generations, and even better physical lookup, physical uncountable functions, PUFs, and also processing using DRAM is not processing using memory is not restricted to DRAM. You can also do those operations in Flash, as Honor mentioned earlier. Again, I'm not going to go into details on all of this, but basically the idea is quite similar. You're going to do multiple word line sensing to do AND operations or operations depending if the data is inside the same block or not. And by doing so, we can accelerate a storage bound operation applications. There are other works that use emerging memory technologies to also do book bitwise operations in DRAM. Pinatubo is one of the first examples. They basically modify the sense amplifiers to sense or to threshold different operations. And finally, those non-volatile memory operations that can use they have this nice property that they can do memory multiplication in constant time by using current-based processing using memory operations. So basically here, the idea is to use Kirchhoff law to do dot product operations. Again, I'm not going to go into details of this. So this was very quick, but I didn't want to delay Atterberg's talk. Hopefully you got the dish that what you can do with processing using memory. Is there any question related to all of this? didn't. We didn't try those. They should be able to do the same operations because the DRAM cells operate the same way. It's just the organization that is a bit different. And the Ambit paper, we did the analysis with at the time was HMC, so like HMC based PIM. For the other ones was all the DDR4 or 5. But then any for the real experiments on commodity off-the-shelf DRAM chips, currently our infrastructure only supports DDR4 ones. Actually, we can do something with HBM as well, but we didn't try it yet. But so far is mostly for DDR4 devices. Okay, thanks so much for the questions. I'm going to move to Atterberg's talk.
Looks nice. So I'll talk about two infrastructures we developed, mainly for processing using memory research. One of them is more general purpose than the other, and hopefully that will be clear as I make progress in the slides. So this is me. I'm a fourth-year PhD student at Sapphire Research Group, and these are my research interests. But I'm gonna skip these fast in the interest of time. So I'll be discussing 4 papers if time permits, but you don't need to know them in detail. Just for you to recall, we're looking at processing using DRAM mostly. That's where we're exploiting the analog computation capability of DRAM chips to realize new functions. So the first paper I would like to talk about is PiDRAM. It's an FPGA-based framework for end-to-end evaluation of processing in DRAM techniques. So I'll start with a summary, but then I'll dive deeper into PiDRAM. So we've seen a lot of commodity DRAM-based PIM techniques, those that we can perform in real DRAM chips. They can improve performance and energy efficiency at no additional DRAM cost, basically. But there are challenges of integrating these techniques into real systems, and we've talked about some of them. And our goal in this work was to develop a flexible framework that would allow us to solve these system integration challenges and evaluate them end-to-end in a real system. So for that purpose, we developed PiDRAM. It's an FPGA-based framework that enables these studies, basically. And we evaluated PiDRAM using 2 processing in DRAM techniques. The first one is RowClone in DRAM bulk copy operations. We've seen that. And for RowClone, we see significant speedups, although part of the reason why is because the processor core we have in the system is wimpy, as Onur mentioned. But the good thing is we can do this case study with only a few hundred lines of Verilog and C++ code, which hopefully is nice. And the second case study we did is to look at the end-to-end integration of a DRAM-based true random number generator. And I'll talk about them in more detail in the upcoming slides. So I'll skip this background information because we've already covered it as part of the other talks in the workshop. I was going to talk about how you operate your DRAM chips and how they're organized, but you already know about these. So I'll skip them. And yeah, so commodity DRAM-based PIM techniques use operational principles of basically commodity DRAM chips to move data and perform computation inside the DRAM array or inside the DRAM chip. And 2 relevant examples are row copy in DRAM bulk data copy operations and true random number generation. There are other functions, and we've discussed them in other talks. But we're going to focus on these 2.
So I'm just going to remind you the key idea of RowClone here. We have the source row in orange color and the destination row in the gray color in the slide. We'd like to move the source row to the destination row. So for that, we activate the source row that moves the source row to the sense amplifiers or the row buffer. And then we need to move this back to the destination row. Now, the first step is already done by basically the standard activate command. So this is already supported by DRAM chips, real DRAM chips. But the second one, we'll see how we can do it without modifying the DRAM chips in the next slides. So we use this carefully created DRAM command sequence, the way we describe carefully them as carefully created DRAM sequences. It's basically an activate, pre-charge, activate command sequence. But you reduce the timing parameters or the delays between those commands to a point where you violate the DRAM standard. This is based on also what Compute DRAM demonstrated in Micro 2019. We adopted this way of performing row clone operations. So this is a pictorial diagram of what happens. Basically, if you use standard DRAM timings and activate the source row S, then pre-charge the bank, and then activate the destination row D, basically you will have activated row S, then pre-charge the bank and activated row D. But if you violate the timing parameters, that's to say, move the commands closer in time, what ends up happening is you activate row S, and immediately after that, you activate row D. So this will allow you to basically get the data back to the destination row without pre-charging the sense amplifiers and losing the data in the sense amplifiers. As for in-DRAM to random number generation, again, I'll try to pictorial describe what we're doing here. This diagram depicts a bunch of cells in a DRAM subarray, and we size and color these cells according to the probability of failure when we access them with a reduced access latency. So we activate the row, and then we wait for a varying amount of time, and then we access this cache block. And if that access yields an error with a very high probability, that's a red cell. And if that operation yields an error with a very low probability, then it's a green cell. Now, the key idea here is basically there are some cells that have a 50% chance to fail when we do this. And we say that because this operation already exists in DRAM chips, we can already access data with reduced access latency in DRAM. This operation is already supported by DRAM chips. So our idea is to leverage this. So we've seen a bunch of nice processing in memory or using memory techniques that can improve system performance, right? So at the application level, let's say we have some application that wants to do bulk data initialization, and we want to back this up with in-DRAM row copy operations. How do we bridge this gap in the system stack is what we're trying to answer with PiDRAM. So you will likely need some support for custom timing parameters, because that's what we require to make both of these operations work. You need some control logic for processing in memory operations in the microarchitecture level. You need to expose this to the programmer via a software interface. And then you probably need a supervisor software support to provide basic system support. Geraldo talked about it in the previous talk. We have some data mapping and alignment requirements that we need to satisfy, and we're hoping to leverage some system support for that. So PiDRAM aims to bridge this system gap with customizable hardware-software components and allow users to rapidly implement processing and memory techniques and solve system integration challenges and evaluate techniques end-to-end. PiDRAM has 4 key components. On the hardware side, we have a PIM operations controller that basically controls PIM operations, another component that has support for custom timing parameters. And the software side, we have a library for application programmers to use and a custom supervisor software that provides basic system support. We attach these components to a real system. So these are the components that we have. And these are attached to basically a rocket chip. It's a RISC-V-based processor design, along with a real DRAM module. This is the full system design of PiDRAM. But I'm not going to go into the details of each component in the interest of time. we basically put this system, download it into this FPGA in the picture you see, and in that FPGA is connected to this DRAM module under the cage. You cannot see it, but that's where we perform the processing using memory operations, processing using DRAM operations. And these are some parameters of the system that we implement. It's a simple in-order core with some cache, and the PIM-enabled DIMM. We have the module number here if you're interested. So to implement RowClone, just to remind you, we violate DRAM timing parameters. We bring the commands together in time. For that, we need to extend the PiDRAM memory controller to support this DRAM command sequence and expose this operation to the user through PIM-lib modification. This is the PIM operations library. This takes us only 198 lines of Verilog code on top of what PiDRAM provides as an extensible basis. And then we study the challenges in implementing or integrating RowClone into a system end-to-end. The first challenge we identify is that we need proper memory allocation for RowClone operations. Because RowClone operations will operate data in DRAM, the data structures basically must be allocated properly to fit in the right place. And I'll get to that in the next slide. And the second problem is memory coherency. Basically, we're operating data in DRAM, so the data that we're operating on should not have any cached copies that would violate the end result. So to solve the second challenge, back then, the RISC-V system did not provide CL flush instructions, so we implemented that. So that's another sort of contribution. I don't know if this is a contribution anymore. With the newest RISC-V based systems, you could integrate PiDRAM with, but we implement CL flush instructions basically and flush the cache lines of the source and destination operands before we perform RowClone operations to solve this challenge. As for the first challenge, we identify 3 memory allocation requirements. This is a simplified diagram, basically, of a DRAM chip with multiple banks and multiple subarrays. And here are some mappings in red that don't work. So if you want to copy source 1 to target 1, you have a problem because your operands should ideally occupy the DRAM row completely, because when you do a copy operation, you're going to overwrite this data here with the data here, which is something you wouldn't want to do. The second problematic allocation is this one, where your operands are not aligned with respect to the bit lines in their own rows. Basically, you need the same bits of the 2 operands on the same bit line. Otherwise, you're not going to be able to copy your source to the destination row. And of course, your source and destination rows must be in the same subarray, because you cannot copy beyond sense amplifier boundaries. Your data cannot move across subarrays or banks with this full parallel operation of RowClone. Now, the fourth mapping here satisfies all 3 requirements, and this is what we aim to have. For that, we implement a new memory allocation function in the custom supervisor software. Basically, the goal of this function is to allocate virtual pages that are mapped to the same DRAM subarray and that are aligned with each other, so that we satisfy mapping 4 in the previous slide. This is what the function looks like. It's the semantics of the function and the parameters that it takes. It's very similar to malloc with the addition of an ID parameter. You supply this ID as the programmer for allocations you'd like to end up in the same subarray. So basically, if you have if you have an array that you would like to map to subarray 0, quote unquote, you would call this function. There is a subarray mapping table, of which I don't go into details for because we don't have so much time, that the system queries and gets the physical addresses that point to that subarray. And then you update the page table using that address. So for more details, I'll have to refer you to the paper, but I'm happy to take questions also. Otherwise, yes. Mm-hmm. Mm-hmm. Yeah, that's a good question. So it's both yes and no. So first, as long as they're in the same subarray, we didn't see an effect of the distance between the two rows affecting the reliability of the operation. If they're across different, well, if they're in different subarrays, then you cannot do it. The way we figure out if they're in the same subarray or not is we sort of do a reverse engineering study. Basically, you execute that activate, precharge, activate sequence for many combinations of addresses. And if only you get the correct result, you determine them to be in the same subarray. Yeah. So then I'll move on to how we evaluate this end-to-end implementation. So this table depicts, again, the system configuration we have. It's a simple in-order CPU core. We execute two micro benchmarks, well, two different sets of micro benchmarks per se. We have CPU copy and RowClone copy. RowClone copy obviously uses RowClone operations, and CPU copy uses load and store instructions in the Rocket core. We evaluate RowClone copy with and without CL flash, and hopefully that will be more clear in the next slides. We also have some real, more real workloads, fork bench and compile. These are respectively copy and initialization heavy workloads that we evaluate in PiDRAM. And finally, we also managed to make libquantum work in this like run it end to end in this infrastructure. And we replaced the colloc calls, which allocate basically data with a given sort of data pattern with in-DRAM initialization operations. And we have 8 kilobyte rows in our DRAM chips or DRAM module that determines the copy granularity. So you cannot copy less than 8 kilobytes at once. So this shows you the throughput improvement we get for initialization and copy operations. So this is RowClone copy over CPU copy and RowClone initialize over CPU initialize. Then we don't have any CL flash operations. So we basically assume that all data is up to date in DRAM, no cached copies. That gives us a relatively large throughput improvement, but part of this is because the Rocket core is already like not very high performance. And when we involve CL flash operations, when we involve the overhead of coherence, essentially, the throughput improvements dramatically reduce. And this basically shows, on the x-axis, we sweep how the fraction of dirty cache blocks in the data that we copy. We're copying 8 megabytes to another 8 megabytes here. So if it's all dirty cache blocks, we have to evict them. If it's not dirty cache blocks, we still have to invalidate the cached copies. And this is where the overheads are coming from, essentially. That's the conclusion. CL flash dramatically reduces the potential throughput improvement. So this is something you would likely not do. Like you wouldn't fix the coherence problem using CL flash probably. So we need better solutions, I'd say. So I'll summarize the remaining results in this slide, the remaining results for other workloads. So this shows the speed up provided by RowClone operations for the fork bench workload when we use RowClone operations instead of like CPU copy. The x-axis shows you the like different configurations of the fork bench workload, where the number of like the number after the hyphen here indicates the amount of 4 kilobyte pages that we copy after each fork call. And we observe that as the fraction of time spent on copy operations increase, the speed up, like that's the fraction is indicated by the blue curve, the speed up also increases, which is something we would expect. And it goes up to 42.9% for the fork 2K configuration. We run compile as well. For compile, we observe a 9% execution time reduction. And this is, we think, is in line with 17% of the execution time compile spends on initializing its data, basically. And for libquantum, we observe 1.3% end-to-end execution time reduction or speed up. And this is also in line with that 2.3% fraction of time libquantum spends on initializing things. So that's it for the RowClone case study. Now I'll move on to, yes. Yeah. Yeah.
the number of this 2,000 something is related to the size of some subarray or not?
That's a good. It can be dependent so as long as you can map your data to different subarrays and fit all that data, you should be fine. But in this at least in these results, we don't have such a problem. Yeah.
But in order to all data in memory, is that correct?
Yes. So basically, exactly. So 80% of the time, 80% of the time, the fork workload would spend calling mem copy functions, and now we offload that to PM. So the next one we evaluate, the next case study we have is the in-DRAM true random number generation work. The operation. Just to give you the key idea again, we're trying to find these cells and leverage or read them back to back, the cells that fail with a 50% chance, so that we get random numbers out of them to generate large streams of random numbers. The implementation wise, this is very simple. We identify 4 DRAM cells that fail randomly in a cache block. And then we sample this cache block, essentially. We keep accessing this cache block with reduced latency. And this slide is describing that. But the key result is over, again, the baseline or the baseline system design we have. We need 190 lines of Verilog code and 74 lines of C++ code to implement a DRange end-to-end. And we evaluated with some micro benchmark that keeps reading through random numbers. On the x-axis, we have a configurable TRNG period. What I didn't describe in the previous slide is basically you have a configurable knob. The memory controller keeps periodically generating random numbers and store them in some buffer. So you can adjust that period. And if you have an aggressive period, we could go down to 220. This is design limitations of PiDRAM. We can improve this in a new version. There's no fundamental limitations. You get up to 8.30 megabits per second throughput in an end-to-end implementation of DRange in our infrastructure. So that's it for PiDRAM. PiDRAM is completely open source at this link on GitHub. If you're interested, as Onur said, I'll be happy to help you get it running and improving it, obviously. We have an extended version of the conference publication, the journal publication of PiDRAM on archive. And I have a longer talk where I give some sort of a full-blown tutorial on PiDRAM and how to use it, basically. So that's it for PiDRAM. The next infrastructure I want to talk about is DRAM Bender, which is not used just for processing using memory research, but many other works that we do and other people do, but we will get to that. So this is an extensible and versatile FPGA-based infrastructure to easily test state-of-the-art DRAM chips. There are many factors that affect DRAM reliability and latency, and maybe performance, energy efficiency, and so on. You have cell-to-cell interference, manufacturer process variations, temperature, voltage, DRAM timings, and these cannot be modeled properly in simulation or analytically, maybe not properly, but easily. And we need to perform experimental studies using real DRAM chips to gather data and understand these factors that affect DRAM reliability better. There are DRAM testing infrastructures that allow experimental studies of real DRAM chips. 2 open source FPGA infrastructures when we started developing DRAM Bender were SoftMC and LiteX Tester. So they're publicly available and they're relatively low cost, right? Because you can get an FPGA board and start working on it. And you need to pay some money for some DRAM modules, which cost 50, 60 bucks. So it's quite a cheap infrastructure to use and gather insight. Now the limit, they had the open source infrastructures then had limitations such as interface restrictions, which would prevent you from running all sorts of experiments to do all sorts of studies. But I'm not going to go into details of those. Ease of use limitations. SoftMC, for example, was very difficult to get running at that point in time because of legacy software and hardware requirements. Yes, Geraldo's signing me that I have 5 minutes left. Okay, and they had extensibility issues whereby monolithic hardware design prevented users from easily modifying code to add some new features. And our goal with DRAM vendor was to basically get a superior DRAM testing infrastructure developed. And these were our key design goals. So in the end, we have DRAM vendor. It's a publicly available FPGA-based DDR4, DDR3, and HBM2 characterization infrastructure. And it's easily programmable using the C++ API we provide. This is just one FPGA. This was just one FPGA board. We have 5 different prototypes. All of them you can start using. We actually have 7, but I didn't update the slide. You don't see the HBM2 boards we support here. But if you're interested, I would be happy to get in touch with you and describe those details. Anyways, we have a lot of FPGA-based prototypes that are ready for you to use out of the box. We did 3 case studies in the paper we published on DRAM vendor. So those were, one of them was on RowHammer. Sorry, the 2 of them were on RowHammer, and 1 of them was on in-DRAM bitwise operations. These show the flexibility of DRAM vendor. That was our goal, basically. It supports many different types of experiments. And I'll just illustrate the ease of use with one slide and move on to basically conclude almost my slides. So this is the C++ API, how you can use it to write a RowHammer program, which repeatedly activates 2 rows that sandwich a victim row. And that's relatively easy compared to having to, for example, write a new Verilog module that would run this loop for you for testing. And this makes it easy to devise new experiments and run them and gain insight, basically. So there are more details in the paper. I can refer you to the paper for those. And this is like a list of research that DRAM vendor enabled. 2 of them you see, we will present them on Tuesday in HPCA. And there are many other works from our group and many other works from other research groups that DRAM vendor enabled, which makes me very proud of it. Some of them that are relevant to this PIM tutorial, Geraldo already described and Onur already described functional complete Boolean logic in DRAM chips and SIMRA, simultaneous many row activation off the shelf DRAM chips. I won't go into the details of those, unfortunately, in the interest of time. Those were enabled essentially by DRAM vendor. So Ismail took DRAM vendor and some DDR4 modules and ran some bunch of violated timing DRAM commands with violated timing parameters to realize that when you reduce the timing parameters too much between this activate precharge and activate command sequence, you don't only open row A and row B, but you open 16 rows from this sub-array and maybe 16 other rows from this sub-array, depending on what A and B is and what timing parameters you use. And yeah, that enabled NOT operations, NAND, NOR, and OR operations in DRAM chips, in real DRAM chips, basically. And I am just gonna go to the end of my slides and conclude. So again, to summarize, DRAM vendor is the first publicly available DDR4 characterization infrastructure, now also HBM2. It's flexible and easy to use. And it enabled, I think, many studies, ideas, and methodologies in the design of future memory systems. And I hope it continues to do so. And you can find various references to DRAM vendor in this slide. And I'll be happy to answer your questions. You can send me emails, or we can talk after the workshop. That's all, I think, from my side. Do you have any questions? If not, then I yield to Professor John. Yeah. Mm-hmm. The technology node is a good question. So basically DDR4. Yeah. Yeah, I'm trying to find the proper slide. So we have many generations of DRAM chips that come from that obey the same interface. DDR4, for example, would have many various. Yeah, basically that's, I guess, my answer. You can study the revisions, various revisions of chips, but just you need to somehow acquire them. Yeah. Does that answer your question? Maybe we can talk offline also. Yeah. Yeah. Thank you.
So, my name is John Kim. Oh, no.
We normally also have invited speakers in Memory-Centric computing workshop. Today, we're very happy to have John Kim. John is a full professor at PICE, one of the top schools in Korea. He got his PhD, master's degrees at Stanford, and undergraduate degree at Cornell. He's done a lot of exciting work on interconnection networks. In fact, Dragonfly network is one of my favorites. We use that in the Tesseract paper, if you remember. He's going to talk about, he's also doing work on memory-centric computing. He has a paper coming up at the HPCA, right, on PIMNet. He's going to talk about some, I think, exciting topic on memory-centric versus communication-centric. The debate that's quite interesting. Go ahead, John.
So thank you for the introduction. So I was trying to come up with something interesting. And this is what I came up with in terms of the title. I still don't know what it means. I'm still trying to figure that out, but I'll try to at least make it a little bit interesting. So my focus is more on the interconnection network side of computer architecture, not sort of memory, but I've sort of dived into memory aspect as well. But having said that, I work on interconnection networks, and you would like to argue that it's the most important part. But I would argue it's perhaps the least important, but it's also the most critical part. And I think the difficulty or challenge of speaking at this workshop is everything was covered. Everything you ever wanted to learn about PIM has been mentioned in one way or another by the speakers today. So it's really hard to follow that up. So I'll try to add a little bit of different flavor. I think that's perhaps what I'll try to do, coming from a slightly different perspective in terms of how I've focused on sort of communication aspect. So having said that, I think it would be foolish to sort of try to introduce memory-centric computing. So I just grabbed this picture from the tutorial today, but I think this was mentioned today as well. It's not really about memory, it's more about data, right? I think so everyone would agree. Is it memory-centric or is it data-centric? I think people would say it might be the same thing, but again, the key focus is on data. But having said that, I like this picture that HP used when they were talking about memory-driven computing. They call it memory-driven computing. I think it's essentially the same thing as memory-centric computing. So what people talk about in terms of processor-centric is what's shown here on the left, right? You have essentially processors, the compute part sitting in the middle, and the memory sort of going around. And what they call memory-driven computing is shown here on the right. So you have the processor on the outside and then the memory in the inside. But I want you to focus on, there's two aspects here. There's the memory aspect. But in addition, they call it a fabric, you call it a network or whatever you want to call it. You need that fabric to interconnect the memory and the compute parts together. I think the part that people often overlook is that you're always going to have a fabric. You're always going to have a network. The only thing is, are you going to really notice it or not? And the sad part about the network part is, if you don't notice it, it's not a problem. You don't really have to worry about it. But people start noticing it when it really does become a problem. And then you really have to worry about it. So again, I came up with the title, is it memory-centric or communication-centric? I still don't know what it means, so what do? I asked ChatGPT. And this is where you shouldn't rely on ChatGPT. It gave me some answers. I didn't know what it means here as well. It says communication between computing elements rather than just processing power. So this clearly, ChatGPT clearly does not know what processing power here means. But I think the second part was really wrong as well. It says this approach is relevant only for large-scale distributed systems, cloud computing, and so forth. Again, that's only part of the answer. When we talk about interconnection network, I grabbed the slide from lecture slides that I often use, is that interconnection networks are found in every sort of systems where you have two or more components talking with each other. Again, it could be on chip, it could be within a processing element, it could be obviously within a supercomputer. And that's where I think communication or interconnection networks begins. And here's my definition of what I think communication-centric is. First, I think communication is always involved. It's just whether you notice it or not. The second part here is when communication or data movement becomes a problem. I think if it's not a problem, then there's really no need to worry about communication. But at some point, it will be a problem. And the key word here, I think, to summarize everything that was said this morning, it's not about memory, it's not about data, it's about data movement. But what I would add on top of that, it's all about exposed data movement. What I mean by that is you could have data movement, but if it all goes around, happens in the background and no one notices it, well, it's not really a problem. There are problems in terms of energy efficiency and so forth, but in terms of overall performance, well, it's not really a problem. It's only when it becomes exposed is what I wanted to highlight here. Now, having said that, I'm gonna, like I said before, I wanted to try to propose processing and memory in a slightly different manner. So again, this is another slide I take out from my computer architecture class, and you tell them that there's three aspects of computing system, right? There's the processing part, there's the memory, and there's the communication. And you talk about how things have evolved, processing, you have all these accelerators, different types of storage, and so forth. This is not new. But I think what has changed recently is that, so the part that I want to focus on is sort of the communication, which is nothing more than moving bits around. But what has happened historically is that these three components often were looked at individually. So you have people looking at processing, you have people looking at memory, and then people looking at network as well. But what you see with, especially with processing and memory, is that you're seeing people co-design these components. Again, if you're moving compute to the memory, you're worrying about not only the compute, but also the memory as well. So if you sort of start to merge these together and you're sort of blurring the boundaries, which I think is an interesting approach, which might be necessary. But when you do that, what I would argue is that you're actually overlapping it with communication. And it's really, really hard to ignore what's happening in terms of communication. So having said that, here's sort of the outline for the rest of the talk. I've talked about sort of introduction to what I think communication-centric means. I'll talk a little bit about domain-specific systems architectures. So I think all of you know what domain-specific architectures are, but I'll try to explain why I bring that topic in. And then again, we talked about data movement, so I'll talk about two different examples in terms of memory-centric computing, where you want to try to minimize data movement, and how you want to sort of try to potentially optimize data movements. So again, I think to this audience, I don't need to talk about this slide. You've seen this in textbooks, in many different talks where you look at the trade-off between CPUs and ASICs. And then you have GPUs, FPGAs in the middle. And people often refer to the ASICs here today as domain-specific architecture, right? Again, a one-sentence summary here is that it does a few tasks, but does it very well. Now, again, everyone knows this. I'm not going to talk about this, but again, if I go back to this picture earlier, the upper left here is essentially domain-specific architecture, and that's what people are working on today. Now, there's two other aspects here. There's the memory and the network. Well, does it make sense to have domain-specific memory or domain-specific networks? And my answer to that is that that's what people are doing today. So if you go back to all the PIM work that was talked about earlier this morning, and if you even go back to the Hot Chips presentation that was made a couple of years ago, if you look carefully at the title, they actually use the phrase domain-specific memory. Because again, it's based on GDDR memory, but it's actually targeting one particular application, actually one particular kernel, which is matrix vector multiplication, right? That's what it's targeting. It's not a general purpose memory, or it's not even a general purpose PIM architecture. So having said that, I think this is an interesting way of sort of summarizing all the different types of PIM architectures that you see out there. Just like how we had with domain-specific architectures or processors, you could have different trade-offs in terms of flexibility and efficiency. Fortunately, I think all these architectures were touched upon this morning, but I just wanted to organize it in a slightly different way. You have the UPMEM architectures, which has the general purpose compute as perhaps the most flexible type of PIM. And on the other end, you probably have the Hynix AIM architecture, which is the least flexible, but perhaps the most efficient. And then you have sort of the other sort of variants from Samsung somewhere in the middle. So I would argue that you have domain-specific architectures, but you do have domain-specific memory. Now, again, I focus a lot of my work on the network interconnection networks, and we sort of put together this slide as well that talks about how the different types of networks that have been built have become a lot more domain-specific. Yes. Yeah. Flexible. Sorry, that was.
Flexible electronics, flexible memory.
Oh, sorry. I think the better word here is programmability. Programmability. Yeah. So again, the AIM architecture only allows you to do a particular operation. The UPMEM is effectively a simple RISC core, so you could do various different operations. The Samsung HBM is a little bit more programmable. So it's little bit more programmable than the AIM, but not a general purpose. Yes. So it's flexibility more in terms of programmability. So we took that same definition, we also apply it to networks. You could apply it in terms of different types of networks that have been built. You have general purpose networks, Ethernet type of networks, which gives you a lot of flexibility, but it's really not necessarily the most efficient. If you look at various different specialized systems that have been built, you would argue that they have domain-specific networks. They only work in their particular system, and it's super efficient for their needs, but it's not going to be applicable to everything else. And you could think of what the networks that have been built by NVIDIA somewhere in the middle. Again, that provides a little bit more flexibility, but maybe not as the same amount of efficiency. So again, given that we're in the area of domain-specific architecture, it makes sense to sort of consider what domain-specific networks would look like as well. And again, these terminologies are not super new. This is a ACM article that was published by Google several years ago, and they used the term domain-specific supercomputers for their TPU systems. Again, they have their domain-specific architecture, TPU, as well as their domain-specific networks that interconnects these systems together. So again, that's where I believe systems are heading in terms of domain-specific architectures. And the question that you can ask yourself is, well, how can we try to minimize data movement? Right, so I'm going to talk about two different aspects in terms of minimizing data movement, as well as perhaps optimizing data movement. So while I was sort of preparing for this slide, I actually went back quite a bit. Over 10 years ago, we did this original work where we actually called this memory-centric network. Again, we couldn't come up with a better name, so we came up with a memory-centric network. But what we did was, back then, the HMC technology was available. That was, something that was mentioned earlier this morning. But it's a 3D stacked memory, and you have a logic layer on the bottom. But the key thing that we were focusing on is that you could actually place a router, a switch inside the router that you could connect multiple of these HMCs together. So having said that, how would you organize your system? So if you do it in a sort of a traditional way, this is what you call a processor-centric network, right? So you still have the memories connected to your CPUs like any other a memory system, and then you have your CPUs connected together. What we were proposing back then is a memory-centric organization where you have the CPUs connected to the memory. And now, given that the memory have switches or the routing capability, why not connect them up together through a memory-centric network? So given this notion of a memory-centric network or a memory-centric computing, well, what can you do with that? I think one interesting case study we sort of proposed back then is in sort of a heterogeneous sort of systems. So here's an example of a traditional multi-GPU system, right? You have your CPU, CPU memory, GPU memory, and then you have some sort of interconnect PCI that connects the CPU and GPU together. Now, one of the common operations that occur in these sort of systems is that you do something on the CPU, you offload it to the GPU. Then that means you have to copy something across from the CPU all the way up to the GPU. But that has to go through quite a bit of interface. So you start from the CPU memory, go through the DDR CPU, through the PCI, to the GPU, through the GPU memory interface up to the GPU memory. That's a lot of steps, right? So the question is that really necessary? Right, again, a lot of the things that were talked about this morning talked about minimizing data movements and so forth, but this is sort of at a slightly larger scale. Do we really need all these different types of interfaces? And can we minimize the data movement? So this is where we sort of came up with this notion of a memory-centric network organization, where we sort of unify the memory system between these different heterogeneous types of systems. So if you look at sort of the questions that, or the problems that can occur, is that now that if you have a shared memory system, obviously you could have longer remote memory latency. The question is, well, there's a lot of work on NUMA sort of work where you can try to optimize that. Is there such a standard? So this was an interesting question because back then there wasn't. Today, maybe with the advent of CXL, you know what, maybe this is something that's a little bit more feasible. But let me try to give you a little bit more example of what I mean by unified memory here. So here you might have a GPU system with its own GPU memory network. And then you have your CPU with its own memory. And then you have a CPU and GPU connected with its own memory. So you have essentially three separate networks connecting up this sort of heterogeneous system. Well, the question is, well, do you really need that if you can afford to have a unified memory network? If you do that, then you probably don't need the CPU, GPU, PCI network, and you could communicate through the unified memory network. More importantly, you probably don't even need to copy data across because you can access whatever memory region through that unified memory network that you have. So again, this was a work that we did over 10 years ago. But this sort of concept came back when we were looking at PIM very recently. And this is where we came across this again when we were looking at sort of domain-specific system architecture. So this is when we were trying to accelerate LLM inference. And as everyone knows here, there's different types of kernels that needs to be optimized. You have the matrix operations, and then you have the matrix vector operations. And the matrix is well suited for NPU sort of systolic array type of architecture, whereas the matrix vectors are more suited for PIM architectures. So the question is, can we combine those two? I think that's a very simple approach that many have thought about, but what are the challenges in doing that? So the work we did was actually combining the PIM that was proposed by Hynix, as well as a different NPU architecture that was proposed by a startup in Korea, which eventually got bought out. But what are the challenges when we try to combine these two architectures? So here's an example of how you might sort of interconnect the systems together. You have your NPU, your processing unit. You have its own memory, right? So it obviously needs its memory to do its operation. And then you also have the PIM connected to that. This is what we would refer to as a partition memory system, because you have the memory for the PIM as well as for the NPU itself. Now, if you do that, obviously you have the parallelism available. So the NPU can be accessing its memory while the PIM can be doing its operations. So that's great. But one of the challenges with a lot of the PIM-based system is memory capacity. And one of the problems with this sort of a partition organization is that you have very inefficient usage of the memory. Why? Because you have to copy data across both from the NPU host memory to the PIM memory itself. And if you look at the work that was published in last year's ASPLOSH here, if you look at the data, quite a bit of the data itself is actually shared across both the PIM and the actual memory itself. So the question is, can we do something better with that? So the same concept that I was proposing earlier in terms of unified memory, can we do that for a PIM-based system? So instead of having dedicated memory, why not just combine that? So we're using the memory within the PIM for both for the PIM acceleration as well as for the memory for the NPU itself. So it obviously gives you a better usage of the memory capacity itself. And we ended up calling it Janus because apparently that's the Roman god's names for someone with two faces or duality. So that was sort of the main approach here. Again, the key thing here is you want to minimize, you want to obviously save the memory capacity, but you also want to reduce the data movement between the different type of memory that would exist when you have this sort of an organization. So that was sort of the key idea that we sort of took with this work. And you can look at the paper for other sort of details. But again, the key thing here is that it was a unified memory system such that you share the memory between the PIM and the NPU, and you avoided the unnecessary data movement. The other interesting aspect is everyone has heard of memory controllers and memory access scheduling. We had to come up with a new catchy name here, so we called it PIM access scheduling, because now the controller is not only responsible for the normal memory accesses to the shared memory unit, but it also has to schedule the PIM commands as well. So that's sort of the new challenges that goes on with this particular system. Now, let me move on and talk a little bit about domain-specific networks in terms of PIM before I wrap up here. When we were doing this sort of exploration, we were using the UPMEM PIM system. And again, I'm sure people have noticed this. I don't know if people have called this, used a different terminology, but we call this term, concept PIM locality. What that means is that everyone knows PIM where you're moving the compute to the memory. And that's a great idea, but it's only for the data that's near the compute. What do I mean by PIM locality? If you look at this red box here, this is again a die photo from Hynix PIM processor. It has a bank memory, and then it has a PU, which is a processing unit. Processing unit can only operate on the data it's located in that particular bank, not any of the other neighboring banks. Similarly, for the picture on the left, that's a cartoon of a UPMEM system. A single PIM chip has 8 banks. Each bank has 64 megabytes of memory, and each bank has a single processing core. The processing core can access the data within its 64 megabyte memory, but once it has to go to a different bank, there's no way of reaching that data. Well, actually, there is. You just have to go back to the host, which is a very inefficient way of accessing data. And it sort of destroys all benefits of what people would say they obtain from PIM. So the question is, what can we do about that? And how problematic is this? So one of the first studies we did was we looked at scalability. So again, this is sort of for different workloads that we ended up writing ourselves. We looked at 2 different types of workloads. One was an embedding table, and the other is what's called a number theoretic transform that's used in homomorphic encryption. The details of the algorithm is not clear, but anytime you look at scalability and performance, as the number of cores increase on the x-axis, you want something linear. And for these workloads, if we're just looking at the compute part, the work that's actually done on the PIM near the memory, it's actually very linear. So, but again, this is just about the scalability performance of the compute aspect, not the entire overall performance of the kernel itself. So if you look at that, it's going to drop. But the question is, well, why does that? Well, I think there's 2 things. One is that you do have to have data movements between the main memory to the PIM memory, which I just talked about before. And there's no way of doing direct PIM to PIM data move. If you wanted to do it, you'd have to do it indirectly through the host. Now, having said that, the work that we're presenting actually is not the first work that have identified this problem. Again, I think you can go back to the PIM benchmarks that were talked about earlier today. They identified this problem. I forgot exactly how they worded it, but it's effectively that you don't have the PIM to PIM communication available. And there's actually been a lot of solutions, a few solutions that have been proposed, but they've been mostly what you would refer to as software-based solutions. What we're trying to propose is that, well, why not introduce a network to the PIM to enable this PIM to PIM communication through, again, what we refer to as sort of domain-specific networks. So again, the next few slides, I have some cartoons about how the challenges here, but I'm going to go through them relatively fast here. Again, if you want to copy something from the host DRAM, you have to move it through the CPU and then copy it over to the PIM RAM. So obviously that's very costly in terms of overhead. And the same applies for PIM to PIM as well. Again, if this DPU wants to access a data from a neighboring DPU, again, there's no way of directly connecting these things together. And again, you have to communicate through the host, right? So that's obviously very inefficient. So again, what is the overhead of that? So here's just some evaluation. Again, this is what I showed you earlier for one of these kernels. If you look at the overall speed up, again, it's not too bad, but obviously you don't get the same nice speed up as you would have wanted before. And for this particular kernel, the key thing here is that if you go to a larger number of DPUs, the amount of inter-DPU or the communications between the DPU themselves actually represents a significant fraction. Now, this is not too bad, but if you look at some other kernels that we looked at, that's not a good thing, right? When your speed up has that sort of a shape. And the problem here is that you have to do a final reduction for this particular kernel, and a lot of that time is actually spent on the host. If you look at a publication that appeared in last year's ISCA, they look at how you can sort of optimize the host side. And again, that can significantly reduce the host overhead. But what I would argue is that that's still inefficient because you still have to go to the host and you still have to come back. So you effectively have to have a 2x bandwidth usage. And the question is, can we do better? So this is where we propose what we call the PIMNet. So again, this is what my student will be presenting on Wednesday here, where you could propose interconnecting the PIM units together, right? So you could have a PIM interconnect at the chip level, at the DIMM level, and across the DIMMs as well. So each of them would have different constraints, different ways of communicating, but effectively, it prevents you from having to go back to the host for communication. Now, again, when you try to introduce this sort of a logic into memory, it's obviously very costly. But I would argue that this sort of interconnect is not new, especially if you look at this picture from what Hynix proposed in terms of their architecture. They actually have a centralized global buffer in the middle shown here. And then they have a whole bunch of global wires that are actually connected to the different various processing units. So they have a centralized way of communicating to all the banks. They just don't have a way of providing the communications between the banks. So again, I would argue it's not the most straightforward way because there are going to be many challenges. There are obviously going to be hardware challenges. I think I want to use the word adoption of PIM. So I just changed that slightly to say adoption of PIMNet. It's not going to be straightforward, but I would argue that the benefit of introducing this sort of an interconnect could be great because it can allow different types of applications to leverage PIM. But again, what are the challenges? Again, in terms of the hardware, you can't ignore the constraints of a DRAM and what that can provide and what it does not provide. So you need to try to exploit that as much as possible. And obviously, you want to make sure it has minimal impact on software. And again, like I said before, we're going to talk about, my student will present the details of this work on Wednesday. If you're going to try to present a general purpose network, that I think would be an overkill and maybe too much to be able to be implemented with DRAM. We focus on one particular aspect of communication, which is the collective communication. So we'll see if that could, the hope was obviously that minimizes the complexity. One last thing. I talked about sort of the communications within a PIM module, within the PIM chip across the different processing elements. The other thing that people should worry about, I think there's a lot more work that needs to be done, is what happens if you try to scale up PIM. One of the things that people have not talked about here is that PIM is great, but it actually reduces memory capacity. And the memory capacity of these systems are not great. So if you want to do any sort of reasonable size problem, if you want to handle that in any sort of efficient way, you have to scale things out. And again, those are some of the things that really has not been explored and something that needs to be studied. And I would argue that you probably don't want to put a general purpose network here. You probably don't want to interconnect these things together with an Ethernet because you're going to lose out on a lot of the benefits of what you have with a PIM-based system. So here's a sort of a summary of what I've talked about. Again, you could call it memory-centric, you could call it data-centric, you could call it communication-centric. I would argue the key thing is it's all about data movements, but like I said at the beginning, it's all about data movements that gets exposed, right? And given that we're living in an era of memory-centric computing, as well as data domain-specific architectures, we should look at them both carefully and see what the opportunities are in terms of minimizing data movements or optimizing them. And again, the two things that, the common terminology people use, people talk about scale-up systems, scale-out systems. I would argue from a PIM perspective, you have the same issue. You have a scale-up issue in terms of how you sort of design a PIM module starting point, but you also have to worry about how you scale these systems out. So I think those are some of the things that needs to be explored. So that concludes my talk, and I would be happy to take any questions.
Okay, maybe one of the things which is correct, memory-centric. Okay, so about unified memory. For me, means unified, let's say, address space.
Mm-hmm.
This is the word.
Mm-hmm.
In the developer or the user has decide in which piece of the memory
Mm-hmm.
will, let's say, store data. Is that the idea of unified memory or something else?
So when we were talking about the unified memory, at least within the scope of this talk, it's essentially physically sharing the memory. So right, yeah. And then you could implement unified memory in terms of on different types of hardware. What I was trying to minimize, what I was trying to talk about here is that if you can physically provide a unified memory, you can minimize any sort of data copying over it. Yeah. So yeah. Mm-hmm.
You have to reorient.
Mm-hmm. No. So but you're right. I think that's one of the challenges is that the data layout. Actually, I think there was a paper in Micro that that developed an accelerator that does that sort of operation. So you could take a look at that.
Thank you, Tom.
Thank you.
Thank you very much. So this gets us to the end of this PIM tutorial. Thanks everyone. Thanks for all of the speakers for the great talks. Thanks everyone for bearing with me and for the very dense, but hopefully instructive tutorial. If you are interested on processing memory, and we have a lot of resources online on the Safari web page. You have the PIM book chapter, a model prime on processing memory available. With recently double in size, so we cover not only DRAM and more, we cover flash, SRAM, all the memory technologies as well. So it's a very nice entry point if you want to do research on processing memory. And you can always contact us here during the conference or via email at any time. We'll be glad to discuss ideas on this direction. So thanks everyone again for joining. It was a pleasure. And that's all. Yes. Hopefully it's better than the previous HPCA.